Tonight we are going to tell you about the epic transformation of our planet, from the fiery birth of Earth to becoming a haven for life. This documentary will take you on a journey through billions of years, exploring how Earth evolved from a scorching ball of molten rock, surrounded by endless lava and volcanoes with no oxygen in the air, to a world where those volcanic forces retreated beneath the surface. The planet cooled and became habitable, and eventually blossomed into a place teeming with animals. We'll delve into the geological wonders, the atmospheric shifts, and the sparks of life that made it all possible, all narrated in vivid detail to bring this ancient story to life. Imagine, if you will, the vast emptiness of space some 4.6 billion years ago. Our solar system is just beginning to take shape from a swirling cloud of gas and dust known as the solar nebula. At its center, a young star ignites, the sun. Around it, particles collide and clump together, forming planetesimals, the building blocks of planets. Earth starts as one of these, a growing mass accruing material through relentless impacts. These collisions generate immense heat, melting the young planet into a seething ocean of magma. This is the Hadean Aeon, named after Hades, the underworld of Greek mythology. For good reason, it was a hellish time. In those early days, Earth was nothing like the blue marble we know today. It was a fiery rock, its surface a continuous sea of lava, glowing red and orange under a sky choked with debris. Temperatures soared to thousands of degrees, hot enough to vaporize rock. Volcanoes weren't isolated mountains as we picture them now. The entire planet was volcanic, with magma bubbling up everywhere from the molten interior. There was no solid crust yet, just a thin, unstable scum on the lava ocean that would crack and reform constantly. The air, if you could call it that, was a toxic brew of gases released from the melting rocks. Carbon dioxide, water vapor, ammonia, methane, and sulfur compounds. No oxygen whatsoever. Oxygen, that life-giving element we breathe so freely now, was locked away in minerals or escaped into space. As Earth grew, the barrage of asteroids and comets intensified. This period, known as the Late Heavy Bombardment, pummeled the planet with massive impacts. Each strike added more heat and material, keeping the surface molten. One colossal event stands out, the collision with a Mars-sized body called Theia. This cataclysmic smash-up ejected debris that coalesced into the moon, but it also reshaped Earth, tilting its axis and mixing its layers. The moon's formation had profound effects, stabilizing Earth's rotation and influencing tides later on, but in the immediate aftermath, it only added to the chaos. The planet's gravity pulled in the debris, and the surface remained a lava world for hundreds of millions of years. Picture the scene, a glowing orb hurtling through space, its surface undulating with waves of molten silicate rock. Bubbles of gas burst forth, creating proto-volcanoes that spewed lava fountains miles high. The heat was so intense that any water delivered by comets vaporized instantly, forming a steamy envelope around the planet. This was a time of pure geology in motion, no life, no oceans, just raw elemental forces forging the world's foundation. Gradually, things began to change. As the accretion slowed and impacts lessened, Earth started to cool. Radioactive decay in the interior provided ongoing heat, but the surface radiated energy into space. The lava ocean began to solidify from the top down, forming the first hints of a crust. This primordial crust was basaltic, dark and dense, floating on the still molten mantle below. But it was fragile, constantly disrupted by convection currents in the magma, which caused upwellings and sinkings, early plate tectonics in embryonic form. Volcanoes during this era were ubiquitous. They weren't the cone-shaped peaks we associate with eruptions today. Instead, they were vast fissures and hot spots where magma poured out in flood basalts, covering huge areas. The planet's interior was differentiating. Heavier elements like iron sank to form the core, while lighter silicates rose to the mantle and crust. This process released more heat, fueling volcanic activity, but as cooling progressed, the volcanoes began to evolve. The widespread lava seas gave way to more localized eruptions as the crust thickened. Now let's zoom in on how these volcanoes entered the center, as our story frames it. meaning how the rampant surface volcanism subsided, with volcanic activity becoming confined to the subsurface and specific vents. It wasn't that volcanoes literally burrowed underground, rather the planet's cooling allowed a stable crust to form, pushing the magma chambers deeper. The mantle, semi-solid and convecting like a slow-boiling pot, drove this. Hot plumes rose, melting rock and feeding volcanoes, but as the crust grew thicker, up to several kilometers, the lava had to travel farther to reach the surface. Many early volcanoes were recycled back into the mantle through subduction-like processes, even in this primitive stage. By about 4 billion years ago, the Hadean was giving way to the Archean Eon. The crust had stabilized somewhat, though still thin and battered. Zircon crystals from this time, the oldest minerals we have, tell us of a world where water might have started to condense. But hold that thought, we're not there yet. The atmosphere remained anoxic, dominated by volcanic gases. Volcanic outgassing was the primary source of these gases, building up a thick blanket that trapped heat, keeping the surface warm even as space cooled the planet. In this infernal landscape, the seeds of habitability were ironically being sown by the very forces of destruction. Volcanic eruptions released water vapor, which would later rain down to form oceans. Carbon dioxide from volcanoes would contribute to weathering processes that regulated climate, but for now it was still a barren, hostile place. No oxygen meant no ozone layer, so ultraviolet radiation from the young sun bombarded the surface, breaking apart molecules and preventing complex chemistry. As we delve deeper, consider the role of the core. The inner core, solid iron, and the outer core, liquid, generated a magnetic field through dynamo action. This shielded the atmosphere from solar wind stripping, preserving the gases that would one day support life. Without it, Earth might have ended up like Mars, airless and dead. The transition from this fiery rock to a more structured world involved immense timescales. Over millions of years, the lava oceans crusted over completely. Islands of solid rock floated on the magma, colliding and merging like proto-continents. Volcanoes dotted these, belching ash and lava, building up layers. But as heat flow decreased, the frequency of eruptions waned. The volcanoes entering the center can be visualized as the mantle's convection cells organizing, with downwelling slabs carrying crustal material back inside, recycling it. This is the birth of the rock cycle, where igneous rocks form, erode, and subduct. By the end of the Hadean, around 4 billion years ago, Earth had a nascent ocean. Comets and asteroids delivered water, and volcanic outgassing added more. As temperatures dropped below boiling point, rain fell in torrents, filling basins. But these early oceans were acidic, hot, and mineral-rich, more like soup than sea. Still no oxygen, the water was anoxic, with dissolved iron and other metals. The atmosphere evolved too. Early on, it was mostly hydrogen and helium, but these light gases escaped. Volcanic contributions shifted it to carbon dioxide and nitrogen dominance. Methane from vents kept it greenhouse warm, countering the fainter young sun. This sets the stage for the next phase, how the planet's surface stabilized, allowing water to persist in the first steps toward habitability. But we're still in a world without breathable air, where volcanoes rule from below. As cooling continued, the crust thickened to about 40 kilometers in places. Plate tectonics kicked in fully during the Archean, with subduction zones where oceanic crust dove back into the mantle, carrying water and carbon with it. This hydrated the mantle, lowering melting points and sustaining volcanism, but now more focused at arcs and rifts. The widespread lava plains of the Hadean became buried under new rock layers, effectively sending those ancient volcanic features underground as part of the geological record. Granitic continents began to form through partial melting at subduction zones, lighter and more buoyant than basalt. These provided platforms above sea level where weathering could start, but without oxygen, weathering was different, no rusting of iron, for instance. The lack of oxygen meant the atmosphere was reducing, favorable for certain chemistries but hostile to modern life. Ultraviolet light split water vapor, allowing some hydrogen to escape and leaving oxygen behind, but it was minimal and quickly reacted with rocks. Life's precursors might have stirred in hydrothermal vents at mid-ocean ridges where volcanoes met sea. These black smokers, powered by mantle heat, spewed minerals and created energy gradients for organic molecules. But we're getting ahead. The planet was becoming less volatile, with volcanoes now channeled through specific conduits rather than blanketing the surface. The entering the center symbolizes this shift from global melt to localized magma reservoirs deep in the crust and mantle. As the Archean progressed, the first supercontinent, Valbara, assembled. Volcanoes built island arcs that collided, forming landmasses. The oceans cooled and simple cyanobacteria-like organisms may have appeared, but oxygen was still absent. Let's begin at the very beginning, when the Earth was nothing more than a fiery rock, a seething mass of molten material in the vastness of space. About 4.6 billion years ago, our solar system was born from a massive cloud of gas and dust called the solar nebula. As this cloud collapsed under its own gravity, the center ignited to form the sun, and the remaining material spun into a disk. Particles within this disk collided and stuck together, forming larger bodies called planetesimals. These planetesimals smashed into each other, building up heat through friction and gravitational compression, eventually coalescing into the proto-Earth. In those earliest days, the young Earth was a hellish place, a glowing orb of lava. The surface was an ocean of molten rock, with temperatures exceeding 2,000 degrees Fahrenheit. Volcanoes weren't discrete features. The entire planet was volcanic, with magma welling up from the interior everywhere. The heat came from several sources: the energy of accretion from all those collisions, radioactive decay of elements like uranium and thorium, and the separation of the planet's layers as heavier materials sank to the core. This differentiation created a dense iron-nickel core, a mantle of silicate rocks, and an outer layer that was still completely liquid. The atmosphere at this time was thick and toxic, composed mainly of gases released from the molten interior: carbon dioxide, water vapor, nitrogen, ammonia, and sulfur dioxide. There was no free oxygen. It was bound up in oxides within the rocks. The sky would have been a hazy, reddish-brown, lit by the constant glow of lava and frequent lightning storms from the charged atmosphere. Meteors and asteroids rained down, adding to the chaos, each impact vaporizing rock and throwing up plumes of debris that circled the planet before falling back. One of the most dramatic events in Earth's early history was the giant impact that formed the Moon. A Mars-sized object, often called Theia, collided with the proto-Earth at an angle, vaporizing much of both bodies and ejecting a ring of molten debris into orbit. This debris quickly coalesced into the Moon, which stabilized Earth's tilt and rotation, setting the stage for seasons and tides later on. But in the immediate aftermath, the collision only intensified the molten state of the planet, resetting the clock on cooling. For hundreds of millions of years, during what geologists call the Hadean Eon, Earth remained a world of fire. The lava ocean was miles deep, with waves of molten silicate crashing like a fiery sea. Bubbles of gas burst through the surface, creating explosive eruptions that shot lava fountains high into the thin atmosphere. The crust, if it formed at all, was thin and unstable, constantly remelting or being pulled back into the mantle by convection currents. Massive loops of rising hot material and sinking cooler material that stirred the interior like a pot on slow boil. As time passed, the rate of impacts decreased and the planet began to lose heat to space more efficiently. The surface started to cool, and the lava ocean began to solidify from the top. The first crust was basaltic, similar to the rock on the ocean floors today, dark and dense. But it was fragile, prone to cracking and allowing magma to flood out in vast sheets called flood basalts. These early volcanoes were not the majestic cones we see now. They were fissures and vents that poured out lava in quantities that could cover entire continents. This is where we start to see the process of volcanoes gradually entering the center of the Earth or becoming underground. It's not that the volcanoes themselves moved inward, but rather that the planet's cooling and structural changes confined volcanic activity to deeper levels. As the crust thickened, the magma had to push through more rock to reach the surface. Convection in the mantle organized into more structured patterns, with hot plumes rising from the core mantle boundary and cooling slabs sinking. This early form of plate tectonics recycled the crust, pulling old volcanic material back into the interior where it remelted. By around 4.2 billion years ago, the crust had stabilized enough in places to allow for the accumulation of water. Water had been delivered to Earth by icy comets and asteroids during the accretion phase, but in the Hadean heat, it existed only as vapor in the atmosphere. As temperatures dropped below 212 degrees Fahrenheit at the surface, this vapor condensed into rain, torrential downpours that lasted for millennia, filling depressions in the crust to form the first oceans. These oceans were hot, acidic, and rich in dissolved minerals from the volcanic rocks, more like a chemical broth than the salty seas we know. The atmosphere was still anoxic, no oxygen gas. Volcanic outgassing continued to supply carbon dioxide and other gases, creating a greenhouse effect that kept the planet warm despite the sun being 30% fainter than today. Without oxygen, there was no ozone layer to block ultraviolet radiation, so the surface was bathed in harmful rays that would have sterilized any exposed life. The magnetic field generated by the spinning liquid outer core protected the atmosphere from being stripped away by solar wind, preserving these gases for future evolution. As the crust grew thicker, volcanic activity became more localized. Hotspots in the mantle, where plumes of hot rock rose, punched through the crust to form shield volcanoes, broad and gently sloping. Subduction zones, where one piece of crust dove under another, created arc volcanoes, explosive and ash-spewing. The widespread lava seas of the Hadean were now buried under new layers of rock, effectively underground. The mantle absorbed much of the heat, and volcanoes became conduits from the deep interior rather than surface-wide phenomena. Entering the Archean Eon around 4 billion years ago, the Earth was starting to look more like a planet than a fireball. Continents began to form as granitic rocks, lighter than basalt, accumulated through repeated melting and cooling at subduction zones. These early landmasses were small, like islands in a global ocean, and heavily volcanic. The oceans covered most of the surface, and the water cycle began: evaporation, clouds, rain, runoff, eroding the rocks and carrying sediments to the sea. Still no oxygen. The atmosphere was a mix of nitrogen, carbon dioxide, methane, and trace gases. Methane, produced by volcanic vents and early microbial activity, though life was just beginning, added to the greenhouse warmth. The lack of oxygen meant iron in the ocean stayed dissolved rather than rusting out as it does today. The transition to habitability was gradual. Cooling allowed stable oceans, and weathering of rocks by rain and waves began to draw down carbon dioxide, regulating climate. Volcanoes continued to play a key role, releasing nutrients and gases, but now from deeper sources. The entering the center was complete in the sense that the planet's volcanic energy was internalized, sustained by mantle convection rather than global melt. Hydrothermal vents on the ocean floor, powered by volcanic heat, became crucibles for chemistry. Here, minerals catalyzed reactions, forming organic compounds, the building blocks of life, but the world was still harsh, with frequent earthquakes, tsunamis from impacts, and toxic waters. As the Archean advanced, the first signs of life appeared: simple microbes, anaerobic bacteria that thrived without oxygen. They metabolized using sulfur or iron, clustering around vents. These organisms began to alter the planet, setting the stage for the next great change. The Earth was cooling, the volcanoes tamed beneath the surface, and the foundations for habitability laid. But oxygen was still missing, and the path to a world for animals was long. As we pick up from the cooling of the early Earth, with its volcanoes now channeling their fury from deep within the mantle rather than blanketing the surface in endless lava, we enter the heart of the Archean Eon. This era, spanning from about 4 billion to 2.5 billion years ago, marks a pivotal shift. The planet's transition from a barren, fiery rock to one with stable oceans, emerging landmasses, and the first whispers of life, all still in an atmosphere devoid of oxygen. The volcanoes, once rampant across the global lava seas, had effectively entered the center, their activity confined to subsurface magma chambers and specific eruption sites driven by the mantle's slow, convective churn. This internalization allowed the crust to thicken and stabilize, setting the foundation for habitability. Imagine the Archean Earth, a world dominated by vast, shallow seas covering nearly the entire surface, with small, volatile continents poking through like scattered islands. These continents were built from volcanic arcs where subduction zones melted descending crust to produce lighter granitic rocks. The oceans were hot, around 140 to 176 degrees Fahrenheit, infused with minerals from hydrothermal vents, black smokers spewing superheated water rich in iron, sulfur, and other elements. The atmosphere remained thick with carbon dioxide, methane, and nitrogen, creating a potent greenhouse effect that compensated for the faint young sun. No oxygen meant no blue skies. The air was hazy, tinged with the reddish hue of scattered light, and ultraviolet radiation poured down unchecked, energizing chemical reactions in the waters below. Volcanic activity, though subdued compared to the Hadean, was still the planet's heartbeat. Mid-ocean ridges where new crust formed as plates pulled apart were lined with volcanoes that extruded pillow lavas, bulbous formations hardening underwater. Island arc volcanoes exploded with andesitic lava, building chains that collided to form larger landmasses like the ancient craton of Kopval in what is now southern Africa. These eruptions released gases that replenished the atmosphere and oceans, including water vapor that condensed into rain, feeding the water cycle. But crucially, the volcanoes were now underground in essence. Their roots extended deep into the mantle, with magma rising through conduits rather than from a universal melt. This shift was driven by declining heat flow. The planet's interior cooled at a rate of about 100 degrees Celsius per billion years, allowing the lithosphere, the rigid outer layer, to thicken from a few kilometers to tens of kilometers. The lack of oxygen defined everything. In an anoxic world, chemical processes were reducing rather than oxidizing. Iron dissolved in the ocean stayed in its ferrous form, giving the waters a greenish tint. Methane from volcanic vents and early microbes lingered, warming the climate. Without oxygen, there could be no complex life as we know it, but this environment was perfect for the origin of life. Scientists believe life emerged around 3.8 billion years ago, perhaps in those hydrothermal vents where volcanic heat met seawater. Here, mineral surfaces catalyzed the formation of organic molecules, amino acids, nucleotides from simple precursors like carbon dioxide and hydrogen. The RNA world hypothesis suggests self-replicating RNA strands formed in these alkaline vents, protected from UV by the water depth. The first life forms were prokaryotes, simple, single-celled bacteria and archaea. They were anaerobes, thriving without oxygen, using chemosynthesis to harness energy from minerals. Methanogens produced methane as a byproduct, enhancing the greenhouse effect. Others reduced sulfur or iron. These microbes formed mats on the ocean floor, stromatolites, layered structures of sediment trapped by their biofilms. Fossilized stromatolites from this era, like those in Western Australia's Pilbara region, provide our earliest evidence of life. They altered the environment subtly at first, binding sediments and influencing local chemistry, but their impact would grow. As the Archean progressed, plate tectonics ramped up. The mantle's convection cells drove continents to drift and collide, forming the first supercontinent, Volbara, around 3.6 billion years ago. Volcanism at these boundaries released nutrients, fostering microbial blooms. The crust's recycling through subduction buried more volcanic material, enriching the mantle with volatiles that would fuel future eruptions. Weathering on the emerging lands drew down carbon dioxide as rainwater reacted with silicate rocks to form carbonates that sank to the seafloor. This regulated the climate, preventing a runaway greenhouse like on Venus. Yet the planet was far from habitable for animals. The oceans were toxic with high levels of heavy metals, and the atmosphere's methane and ammonia made it inhospitable. Frequent impacts still scarred the surface, though less intensely than before. The moon, stabilizing tides, helped mix nutrients in the seas, aiding life's spread. Around 3.5 billion years ago, cyanobacteria evolved, photosynthetic microbes that used sunlight to split water, releasing oxygen as waste. This was the spark of the Great Oxidation event, but it wouldn't fully ignite until later. Initially, the oxygen reacted with dissolved iron, precipitating out as banded iron formations, vast red layers in the rock record, like those in Minnesota's Iron Range. These formations locked away oxygen, keeping the atmosphere anoxic for another billion years. Volcanoes continued to outgas reducing gases, countering the oxygen buildup. The Earth's habitability crept forward. Stable continents provided niches for microbial colonies on land, though sparse. The water cycle matured, with evaporation cooling the surface and rain eroding rocks, creating soil's precursor to fertile ground. Volcanic ash fertilized the oceans, sparking productivity. By the late Archean, around 2.8 billion years ago, oxygen levels in shallow waters rose locally, allowing the first aerobic metabolisms. But globally, the air remained oxygen-free. The volcanoes, now fully integrated into the tectonic system, erupted in cycles, quiet periods punctuated by massive flood basalts, like the Fortescue Group in Australia, covering thousands of square miles in lava. This era laid the groundwork, from a volcano-dominated fiery rock to a water world with life. The underground volcanoes sustained the system, pumping heat and materials. As we approach the Proterozoic Eon, the stage is set for oxygen's rise, transforming habitability. The journey continues. Oxygen's arrival would change everything, paving the way for complex life and animals. As the Archean Eon drew to a close around 2.5 billion years ago, the Earth had already traveled an immense distance from its original state as a completely molten, volcano-covered fireball. The relentless surface volcanism of the Hadean had long since retreated. The majority of magmatic activity was now channeled through deep conduits rising from the mantle, feeding discrete volcanic systems rather than flooding the entire globe in lava. The planet possessed permanent oceans, drifting proto-continents, a functioning water cycle, and widespread microbial life, all of this occurring in an atmosphere that still contained effectively zero free oxygen. The next chapter, the Proterozoic Eon, would see the most dramatic chemical transformation in Earth's history. The slow, then explosive rise of oxygen that would fundamentally reshape the surface, the oceans, the atmosphere, and the possibilities for complex life. This period, stretching from approximately 2.5 billion to 541 million years ago, is often called the boring billion in popular accounts because, from a human perspective, surface conditions changed relatively little for long stretches. Yet beneath that apparent stability lay one of the most consequential revolutions in planetary history, the Great Oxidation Event, or GOE, followed by a series of additional oxygenation pulses that eventually produced breathable air. The volcanoes, already underground in the structural sense we have been tracking, played a dual role during this transformation. They continued to supply reducing gases that delayed oxygen buildup for hundreds of millions of years, while simultaneously helping to create the tectonic and nutrient conditions that allowed photosynthetic life to proliferate and eventually overwhelm those reducing buffers. Let us picture the early Proterozoic world. The supercontinent Kenorland had largely assembled by around 2.7–2.5 billion years ago from the collision of smaller Archean cratons. Vast shallow seas covered much of its margins. Stromatolite reefs built by cyanobacteria mats grew in sunlit coastal waters, sometimes forming structures tens of meters thick and extending for hundreds of kilometers. These microbial communities were already performing oxygenic photosynthesis, using sunlight, water, and carbon dioxide to produce organic matter and release molecular oxygen, O2, as a waste product. In the modern world, we take oxygen for granted, but its appearance was profoundly disruptive. Oxygen is a powerful oxidant. In an anoxic ocean rich in dissolved ferrous iron Fe2, any O2 produced reacted immediately with that iron to form ferric iron Fe3, which is insoluble and precipitated as iron oxides, hematite Fe2O3 and magnetite Fe3O4. For roughly the first 300 million years after cyanobacteria appeared, almost all the oxygen they generated was consumed by this reaction. The result was the deposition of enormous banded iron formations, BIFs, alternating layers of iron-rich chert and iron oxides, some of which are tens to hundreds of meters thick and stretch across thousands of square kilometers. Major BIFs from this interval include those of the Hamersley Basin in Western Australia, the Transvaal Supergroup in South Africa, and the Labrador Trough in Canada. These deposits represent one of the largest concentrations of iron ever formed on Earth. During this oxygen sink phase, atmospheric O2 remained vanishingly low, perhaps 10 to 10.3 of present levels. Volcanic outgassing continued to release large quantities of reducing gases. Hydrogen, carbon monoxide, sulfur dioxide, and especially methane produced both abiotically at mid-ocean ridges and biotically by methanogenic archaea. Methane is a strong greenhouse gas. Its atmospheric lifetime was much longer in the absence of oxygen, no hydroxyl radicals to destroy it, so even modest fluxes maintained a warm climate despite the still faint sun. Around 2.45–2.32 billion years ago, however, the balance tipped. Several processes converged to exhaust the primary oxygen sinks. Most of the dissolved ferrous iron in the surface oceans had already been oxidized and buried in BIFs, so new oxygen molecules began to escape reaction with iron and accumulate in the water column. Increased continental weathering, driven by the exposure of more land during the assembly and partial breakup of Kenorland, delivered more sulfate to the oceans. From the oxidative weathering of pyrite in older rocks once trace oxygen appeared. Sulfate-reducing bacteria then produced hydrogen sulfide, which reacted with remaining ferrous iron to form pyrite, Fes2, burying more reducing capacity. Burial rates of organic carbon increased as microbial mats and early planktonic cyanobacteria produced more biomass, some of which sank and was buried before being fully respired, locking away reducing power and allowing net oxygen release. The result was the Great Oxidation Event proper. Paleoredox proxies, sulfur isotope fractionation patterns, mass-independent fractionation of sulfur isotopes disappears when O2 exceeds roughly 10 pal, chromium cycling molybdenum isotopes, and the appearance of red beds oxidized terrestrial sediments. All converge on a rapid rise of atmospheric oxygen between about 2.4 and 2.3 billion years ago, likely reaching 1/10% of present atmospheric levels, pal, though estimates vary widely. This rise was catastrophic for most existing life. The vast majority of anaerobic microbes were poisoned by oxygen. Many lineages went extinct or retreated to anoxic refugia, deep ocean, sediments, hydrothermal systems. The event is sometimes called the oxygen catastrophe or oxygen holocaust for precisely this reason. Yet it was also the enabling condition for aerobic respiration, which yields far more energy per glucose molecule than anaerobic metabolisms, 38 ATP versus 2 ATP in fermentation. Survivors that could tolerate or utilize oxygen gained a massive competitive advantage. Volcanism's role remained critical. Even after the GOE, large igneous provinces, LIP, enormous flood basalt events erupted periodically. Examples include the voluminous Angeluk lavas, (2, 4 Ga in South Africa, and later events such as the Umkhonto, Ga and Quinawan, (1 Ga provinces. These eruptions injected massive amounts of reducing sulfur and carbon gases, temporarily suppressing oxygen levels and causing transient oxygen whiffs, followed by reversions toward lower O2. The long boring billion, roughly 1.80.8 billion years ago, is characterized by relatively stable but low oxygen, perhaps 110% PAL, with episodic fluctuations tied to these volcanic pulses and to changes in organic carbon burial. During this interval, the Earth experienced the assembly and breakup of the supercontinent Rodinia, (10.75 Ga). Widespread banded iron formations ceased because deep oceans became euxinic, sulfidic rather than ferruginous, and eukaryotic cells appeared. Eukaryotes with their nucleus and organelles likely arose through endosymbiosis. An archaeal host engulfed an alpha protobacterium that became the mitochondrion, 1.6 Ga, granting the ability to perform efficient aerobic respiration. Some lineages later engulfed cyanobacteria, giving rise to algae with chloroplasts, 1.2 Ga. These developments were possible only because oxygen had reached levels sufficient to support the higher energy demands of larger, more complex cells. By the late Proterozoic, 800–541 Ma, oxygen began climbing again in what is sometimes called the Neoproterozoic oxygenation event. Several factors contributed: enhanced organic carbon burial during the cryogenian glaciations, snowball Earth episodes, increased phosphorus delivery from weathered continents after Rodinia rifted apart, and declining volcanic reducing fluxes as mantle heat flow continued to decrease. Redox-sensitive trace metals Mo, U, V, and black shales show a marked increase in availability, consistent with higher ocean oxygenation. By the end of the Proterozoic, atmospheric oxygen is estimated to have reached 10–30% PAL or possibly higher, enough to support the first multicellular animals. The Ediacaran biota, 635–541 Ma, soft-bodied, often frond-like or disc-shaped organisms, appear in the fossil record after the Marinone glaciation. Whether these were early animals, giant protists, lichen-like colonies, or something else remains debated, but their appearance signals that ecological complexity was rising. The volcanoes, now deeply rooted in a mature plate tectonic system, continued to shape the planet. Subduction zones generated arc volcanism, mid-ocean ridges maintained the carbon cycle, and occasional lips perturbed climate and redox state. Yet the era of global lava oceans was unimaginably distant. The Earth had cooled, its surface waters were oxygenated in shallow regions, its continents bore primitive soils, and its oceans hosted increasingly sophisticated ecosystems. The stage was set for the Cambrian explosion, when diverse animal body plans would appear in a geological instant. The long climb from anoxic to oxygen-rich conditions, driven by photosynthetic life and modulated by tectonics and volcanism, had finally made a world suitable not just for microbes, but for macroscopic, multicellular animals. We now cross the most famous boundary in the entire history of life on Earth, the moment when the quiet microbial world of the late Proterozoic gave way, in what appears from our vantage point to be almost the blink of an eye, to oceans suddenly teeming with clearly recognizable animals possessing complex bodies, hard parts, diverse ecologies, and the beginnings of food webs that would eventually support predators, prey, grazers, burrowers, swimmers, and filter feeders in astonishing variety. This is the transition from the Ediacaran to the Cambrian period, and the event we call the Cambrian explosion or Cambrian radiation. By approximately 541 million years ago, the planet had already achieved several of the major preconditions we have been tracking. The surface volcanism that once covered the globe in lava had long retreated into the interior. Magmatic activity was now organized along mid-ocean ridges, subduction zones, intraplate hotspots, and occasional large igneous provinces, all manifestations of a mature, convecting mantle whose heat flow had declined enough to sustain a thick, stable lithosphere. Oxygen had risen through two major pulses, the Great Oxidation Event. 2.3 Ga and the Neoproterozoic oxygenation event 800–540 Ma, to levels estimated between 10% and perhaps as high as 40–50% of present atmospheric levels on the eve of the Cambrian. Shallow oceans were oxygenated, deep waters were at least intermittently so in many basins. The carbonate compensation depth had deepened, allowing widespread preservation of shelly fossils rather than rapid dissolution. Phosphorus and other nutrients were more readily available due to increased continental weathering following the breakup of Rhydinia and the Cryogenian glaciations. The genetic toolkit for building complex multicellular bodies, Hox genes, developmental signaling pathways, cell adhesion molecules, extracellular matrix components had already been assembled in the Ediacaran biota or their antecedents. Yet despite these enabling conditions, animals remained rare, small, and morphologically simple until very close to the base of the Cambrian. Then, within an interval that paleontologists now constrain to roughly 20–25 million years, from ~541 to ~515 Ma, with the most dramatic diversification concentrated between ~530 and ~520 Ma. Nearly all the major bilaterian phyla that exist today appeared in the fossil record, most of them already bearing readily identifiable characteristics. This is not to say that every phylum sprang fully formed from nothing. Precursors undoubtedly existed, but they were either very small, entirely soft-bodied, geographically restricted, or ecologically marginal, until the environmental, ecological, and developmental thresholds were crossed almost simultaneously. The best-known window into this transformation is the Burgess Shale in British Columbia, Canada, deposited ~508 Ma, but equally famous are the Sirius passet fauna of Greenland, ~518 Ma, the Chengjiang biota of Yunnan, China, ~518 Ma, Emu Bay Shale of South Australia, ~514 Ma, and the slightly younger Wheeler and Margam formations of Utah. These exceptional conservat Lagerstätten preserve soft tissues in exquisite detail, thanks to rapid burial in fine muds under low oxygen bottom conditions that inhibited decay. They reveal that Cambrian seas were already populated by arthropods, trilobites, radiodonts, megacherons, fuxianhuids, leanchiliids, isaxiids, priapulid and paleoscolcid worms, labopodians, early members of the onychophoran arthropod lineage, chordates and vetulicolians, early deuterostomes, brachiopods, hyoliths, mollusks, including early cephalopods and bivalve-like forms, echinoderms, ctenocystoids, helicoplecoids, edriosteroids, sponges, cnidarians, ctenophores, and various problematica that do not clearly fit into living phyla. Perhaps the single most iconic symbol of the Cambrian explosion is the sudden appearance and rapid diversification of mineralized skeletons, shells, carapaces, spicules, teeth, sclerites. Small shelly fossils, SSFs, tiny calcitic, phosphatized or agglutinated elements including tubes, cloudina, cinetubulites, cones, anabarites, spines, chancelloria, scales, Wiwaxia sclerites, and early brachiopod shells begin to appear in abundance in the latest Ediacaran, ~550–541 Ma, and then explode in diversity through the Terranuvian series, Fortunian to stage 2 of the Cambrian. By Cambrian age 3, ~521, Ma, most major skeletonized groups are present. The geochemical trigger for biomineralization is widely attributed to a rise in carbonate saturation state in shallow oceans, driven by increased alkalinity from continental weathering and decreased deep ocean carbonate burial during earlier glaciations, combined with ecological pressures, predation, grazing, protection against abrasion, and structural support for larger bodies. Predation is widely regarded as one of the central ecological drivers of the Cambrian radiation. The fossil record shows the sudden appearance of clear evidence for macrophagy, eating macroscopic prey, boreholes in cloudina tubes, repaired shell damage, coprolites containing shell fragments, grasping appendages in radiodonts, Anomalocaris and kin, and trilobite bite marks. Before Ma, there is almost no evidence of animals eating other macroscopic animals. After 530 Ma, such interactions become commonplace. This escalation has been termed the Cambrian arms race. Prey evolve thicker shells, spines, burrowing habits, and mobility. Predators evolve stronger jaws, grasping claws, acute vision. Compound eyes appear in the earliest trilobites and in radiodonts in active pursuit. The ecological theater was transformed from one dominated by passive suspension feeding and microbial mat grazing to a dynamic world of pursuit, escape, and defense. Body size also increased dramatically. Ediacaran macroorganisms rarely exceeded 1030 cm. Many Cambrian animals reached 3100 cm within a few million years, Anomalocaris up to 1 m, some trilobites approaching 70 cm. Increased oxygen availability almost certainly facilitated this. Higher O2 partial pressure allows larger body sizes by easing diffusive limitations across tissues and supporting higher metabolic rates. The presence of hemoglobin-like respiratory pigments in some Cambrian arthropods, inferred from exceptionally preserved soft tissues, further supports this link. Developmental biology provides another lens. The genetic regulatory networks that pattern bilateral symmetry, segment polarity, appendage identity, and organ formation were already present in simple form in Ediacaran organisms or their ancestors. The Cambrian explosion may therefore represent ecological opportunity and environmental permission rather than a sudden burst of genetic novelty. Once oxygen, nutrient availability, predation pressure, and biomineralization thresholds were crossed, existing developmental toolkits were redeployed to produce a much wider range of body plans in a relatively short time. Volcanism continued to shape boundary conditions. The breakup of Rodinia 750-600 Ma and the subsequent assembly of Gondwana 570-510 Ma involved extensive rifting, flood basalt volcanism, and arc magmatism. Large igneous provinces such as the 510 Ma Kalkarinji province in Australia released enormous volumes of CO2 and sulfur, likely contributing to short-term climate perturbations and ocean acidification events that may have stressed ecosystems. At the same time, tectonic activity increased nutrient fluxes, phosphorus, iron to the oceans via weathering of fresh volcanic rocks and hydrothermal input at spreading centers, fueling primary productivity and supporting larger food webs. By the end of the Cambrian 485 Ma, the explosion had largely run its course. Diversity stabilized at high levels, although there would be further radiations, especially among echinoderms and cephalopods in the Ordovician. Most major ecological guilds, predators, prey, deposit feeders, suspension feeders, grazers, were occupied, and the basic template of Phanerozoic marine ecosystems was established. The planet was now unequivocally suitable for animals. The fiery, anoxic, volcano-dominated world of the Hadean and early Archean had been replaced by a blue, oxygen-rich, biologically vibrant world, whose surface volcanoes were confined to narrow belts, and whose deep interior heat drove a plate tectonic engine that recycled carbon, regulated climate, and supplied nutrients over geological time scales. The long climb toward habitability was complete. The age of animals had begun. We now stand at the threshold of the Paleozoic era proper, with the Cambrian explosion having already filled the oceans with an astonishing menagerie of animal body plans. Trilobites scuttled across seafloors, anomalocaridids hunted with grasping frontal appendages and acute vision, brachiopods filtered water through shell-hinged lophophores, early mollusks crawled or swam, primitive echinoderms clung to the substrate or rested on the bottom, and the first chordate-like swimmers darted through the water column. Yet this was still overwhelmingly a marine story. The continents themselves remained largely barren of visible animal life. Soils were thin and poorly developed, weathering proceeded mostly through physical and chemical means, without the biological acceleration that roots and microbial communities would later provide, and the land's surface supported only microbial mats, perhaps occasional lichen-like associations, and very simple fungal networks. The atmosphere, while oxygen-rich compared with the Proterozoic, was still lower than today. Estimates for the early Cambrian range from -10–20% to as high as -30% of present levels in some models, and carbon dioxide concentrations remained elevated, creating a greenhouse climate warmer than the modern one. The Ordovician period, 485–443 million years ago, marks the next major step in the planet's habitability journey. The Great Ordovician Biodiversification Event, GOBE, during which marine animal diversity exploded to levels far exceeding even the Cambrian peak, and the very first unambiguous evidence of animals beginning to colonize the land's surface appears. At the same time, the long retreat of volcanic activity into the deep earth continued. Global-scale lava flooding was now extremely rare, replaced by more focused arc volcanism, rift-related basalts, and occasional large igneous provinces whose climatic and geochemical impacts were profound, but regional or short-lived compared with the Hadean and Archean fire world. The GOBE is one of the most sustained diversity increases in the entire Phanerozoic. Family-level marine diversity roughly tripled between the late Cambrian and the late Ordovician, with especially rapid rises among brachiopods, bryozoans, corals, both tabulate and rugose, crinoids, ostracods, gastropods, bivalves, graptolites, nautiloids, and certain groups of trilobites. Several ecological innovations appeared or became widespread. Reefs built by corals, stromatoporoids, bryozoans, and sponges expanded dramatically, creating complex three-dimensional habitats for the first time. Tiering of suspension feeding communities increased. Organisms lived at different heights above the sediment surface, from recumbent brachiopods and corals to tall crinoid forests and branching bryozoans. Predation pressure intensified further, with nautiloid cephalopods developing straight or coiled shells and active jet propulsion, duraphagous, shell-crushing predators appearing among trilobites and early fish like vertebrates, and drilling gastropods targeting brachiopods and corals. Planktonic ecosystems diversified. Graptolites and chitinozoans proliferated in the water column, supporting larger food webs that included early jawless vertebrates, agnathans such as conodonts and astrospids. This marine revolution was fueled by several coinciding factors. Oxygen levels are thought to have continued rising through the Ordovician, possibly reaching or exceeding modern values in some intervals according to certain proxy records, though debate remains. Increased nutrient flux to the oceans, driven by intense continental weathering during the breakup of Gondwana fragments and the exposure of fresh volcanic and orogenic material, stimulated primary productivity. Large igneous provinces, such as the 460 Ma Baku Large Igneous Province in northwest China and the Ma-Amatian basalts, though the latter straddles the Ordovician-Silurian boundary, injected massive CO2 and nutrients, temporarily warming the climate and enhancing chemical weathering. The supercontinent Gondwana occupied much of the southern hemisphere, with Laurentia, Baltica, and smaller terrains drifting northward. This configuration produced extensive shallow epicontinental seas, ideal habitats for the diversification of benthic and planktonic communities. Sea level reached some of the highest stands of the Phanerozoic during the mid-Ordovician, flooding continental interiors and creating vast, low-energy, nutrient-rich shelves. Meanwhile, the colonization of land began in earnest. The oldest convincing evidence of terrestrial animals comes from the late Ordovician, 450–445 Ma. Millipede-like myriapods and primitive arachnids, scorpion-like forms preserved in marginal marine and floodplain deposits in what is now Scotland, Sweden, and the United States. These arthropods were small, likely detritivores or predators on even smaller invertebrates, and their cuticles were already waterproofed with waxes and proteins. They could breathe air via book lungs or simple tracheal systems, structures that had probably evolved earlier in aquatic ancestors but were now co-opted for terrestrial gas exchange. The terrestrial ecosystem at this stage was still rudimentary. Vascular plants had not yet appeared. The land surface was colonized by non-vascular bryophyte-like plants, liverwort and moss-like forms, early charophyte algae, fungal networks, and microbial crusts. These primitive communities produced thin organic soils, stabilized sediment surfaces, and began to cycle nutrients in ways that would later support more complex food webs. Arthropods likely fed on decaying plant matter, fungal hyphae, and each other. No vertebrates had yet ventured onto land. The earliest tetrapodomorph trackways appear much later, in the late Devonian. The end of the Ordovician, tilde 443 Ma, brought one of the most severe mass extinctions in Earth history, the Ordovician Silurian extinction event. Roughly 85% of marine species disappeared, with especially heavy losses among trilobites, brachiopods, corals, bryozoans, and graptolites. The primary driver appears to have been the rapid onset of the Hernantian glaciation. Gondwana drifted over the South Pole, ice caps grew, sea level dropped by 7,100 meters, shallow shelf habitats were eliminated, and ocean circulation changed dramatically. Cooling reduced oxygen solubility in seawater, creating widespread anoxia in deeper basins. Volcanic activity may have played a secondary role. Some models invoke massive sulfur injections from large igneous events or explosive arc volcanism that increased aerosol loading and cooled the climate further. The extinction was selective. Planktonic and deep water forms suffered less than shallow tropical taxa. Many groups that had radiated during the GOBE were reduced to a few surviving lineages that would later re-radiate in the Silurian. The Silurian period, 443–419 Ma, is therefore a time of recovery and consolidation rather than explosive innovation. Surviving clades diversified again, but at a slower pace. Key developments included the first widespread coral stromatoporoid algal reefs forming barrier and patch reefs in shallow tropical seas. Jawed fishes, placoderms, acanthodians, early chondrichthyans, and osteichthyans appeared and began to diversify. Vascular plants, coccinioid-grade lycophytes and rhiniophytes colonized land, producing the first true stems, leaves, and sporangia, though still very small, a few centimeters tall. Millipedes, centipedes, scorpions, and the first arachnids, spiders, became more abundant on land. Eurypterids, sea scorpions, reached their peak diversity, some growing to over 2 meters long. Volcanism remained an important background process. The closure of the Iapetus Ocean produced the Caledonian taconic Acadian orogenies, generating extensive arc volcanism and granite intrusions. These mountain-building events accelerated weathering, drawing down atmospheric CO2 and contributing to long-term cooling trends that would culminate in later Paleozoic glaciations. By the end of the Silurian, the Earth's habitability had advanced dramatically. Animals occupied both marine and terrestrial realms. Food webs now included primary producers on land, primitive vascular plants, herbivores, detritivorous arthropods, predators, scorpions, centipedes, eurypterids, and increasingly sophisticated marine ecosystems with reef frameworks, jawed predators, and diverse plankton. Oxygen levels were high enough to support active lifestyles and larger body sizes. The volcanoes, long since internalized, continued to recycle carbon and nutrients through subduction and mid-ocean ridge processes, maintaining the long-term stability that allowed complex life to flourish. The Devonian period, 419–359 Ma, would take these trends even further, ushering in forests, tetrapods, and the conquest of land by vertebrates, but that chapter belongs to the next stage of the story. We now enter the Devonian period, 419–359 million years ago, frequently called the Age of Fishes in textbooks, yet that label only captures part of the story. During these 60 million years, the oceans witnessed one of the most spectacular radiations of vertebrate life ever seen. While on land the first true forests rose, root systems began to penetrate deeply into previously barren regolith. Atmospheric carbon dioxide started a long decline, and most momentously of all, vertebrates with limbs and digits first crawled out of the water onto the muddy banks and floodplains. The Devonian is therefore the time when the conquest of land by animals accelerated dramatically, transforming a world that had been almost exclusively marine and marginal terrestrial into one where complex terrestrial ecosystems were beginning to take shape. By the beginning of the Devonian, the planet had already achieved several critical milestones in its long journey toward habitability. The thick, unstable basaltic crust and near-global lava oceans of the Hadean were unimaginably distant. Volcanic activity had been internalized for billions of years. Magma rose only along well-defined plate boundaries, mid-ocean ridges and subduction zones, through intraplate hotspots, or during relatively infrequent large igneous province events. The mantle convection that once drove a planet-wide melt layer now sustained a mature plate tectonic cycle that recycled carbon into and out of the deep earth, helped regulate long-term climate through silicate weathering, and delivered nutrients to surface environments. Oxygen levels after the protracted rise through the Proterozoic and the Ordovician-Silurian recovery stood at roughly 15–25% of present atmospheric levels at the dawn of the Devonian, high enough to support active metabolism in larger animals both in water and, increasingly, on land. The early Devonian Lechkovian to Eocene stages, tilde 419–393 Ma, is dominated by continued diversification of jawed fishes. Placoderms armored, jawed fishes with bony head and thoracic shields radiated into dozens of families, some reaching lengths of several meters. Dunkleosteus, though actually late Devonian, exemplifies the lineage's potential. Acanthodians, spiny sharks, filled many ecological roles, from fast-swimming mid-water predators to sluggish bottom dwellers. Early chondrichthyans, cartilaginous fishes, the ancestors of modern sharks and rays, and osteichthyans, bony fishes, appeared and began to diverge into the ray-finned actinopterygian and lobe-finned sarcopterygian lineages. Among the lobe fins, two major groups are especially important for the land transition: the coelacanths, which survive today as living fossils, and the tetrapodomorphs, fish with robust, fleshy pectoral and pelvic fins containing a series of bones that would later become the humerus, radius ulna, femur, tibia, fibula, and digits. The anatomical stage for terrestrial locomotion had therefore been set long before actual limbs touched dry land. The famous fishapod Tiktaalik rosie, tilde 375 Ma, late Middle Devonian from Ellesmere Island, illustrates the intermediate condition perfectly. A flat head with eyes positioned on top, suggesting it could look upward out of the water, a neck allowing the head to be raised independently of the body, robust forelimb bones capable of supporting weight, and fin rays still present but reduced. Tiktaalik lived in shallow, swampy, distributary channels, environments subject to seasonal drying, where the ability to push across mud or crawl from one shrinking pool to another conferred a survival advantage. True four-limbed vertebrates, the earliest tetrapods, appear in the late Devonian, tilde 380–359 Ma. Forms such as Acanthostega and Ichthyostega, both from East Greenland, show a mosaic of aquatic and terrestrial features. Limbs with digits, Acanthostega had 8 per limb, Ichthyostega 7, yet retained internal gills, a tail fin, and a lateral line system. Their robust shoulder and pelvic girdles indicate they could support their weight on land, at least for short excursions. Trackways from the Holy Cross Mountains in Poland, tilde 395 Ma, and later sites demonstrate that digit-bearing tetrapodomorphs were walking on substrates that were periodically subaerial well before the classic body fossils appear. These animals were almost certainly still tied to water, laying eggs there, breathing partly through gills or skin when submerged, but the threshold had been crossed. Meanwhile, on land, vascular plants underwent their own radiation. The early Devonian saw the spread of rhiniophytes and zosterophylls, small, leafless or sparsely leaved plants with terminal sporangia and simple vascular tissue. By the Middle Devonian, tilde 393–382 Ma, Archaeopterid trees, large, woody plants with fern-like fronds but secondary xylem resembling modern gymnosperms and progymnosperms appeared, reaching heights of 10–30 meters. The first seed plants, pteridosperms seed ferns, emerged in the late Devonian. These innovations, roots, leaves, secondary growth, and eventually seeds, dramatically increased terrestrial primary productivity, deepened soils through root penetration and organic matter accumulation, accelerated silicate weathering drawing down atmospheric CO2, and created structurally complex habitats with shade, litter layers, and vertical stratification. Arthropods responded quickly to these new resources. Millipedes, already present since the Ordovician Silurian, diversified into forms capable of consuming decaying plant matter. Primitive wingless insects, columbolans, archaeognathans, and the first true winged insects, Paleodictyopteroids, mayfly-like forms, appeared in the late Devonian or earliest Carboniferous. Arachnids, spiders, harvestmen, scorpions became more abundant and diverse. The oldest definitive insect wing fossils come from the latest Devonian, tilde 360 Ma, although molecular clock estimates push the origin of winged insects somewhat earlier. The late Devonian also hosts one of the most severe and prolonged extinction intervals in the Phanerozoic, the late Devonian mass extinction, actually a series of crises, Kellwasser, Hangenberg, and several smaller events between tilde 372 and tilde 359 Ma. Roughly 70–80% of marine species disappeared, with especially heavy losses among reef builders, stromatoporoids, tabulate and rugose corals, armored placoderms, trilobites, and many brachiopod and ammonoid lineages. Causes remain debated, but a consensus points to a combination of global cooling and/or episodic anoxia driven by enhanced nutrient input from expanding land plants, increased weathering right arrow higher riverine phosphorus right arrow algal blooms, widespread oxygen minimum zones in oceans. Possible large igneous province activity, e.g., the Villi traps in Siberia, tilde 367–361 Ma, or the Kola-Dnieper lip. Sea level fluctuations and habitat loss. Extraterrestrial impacts, Siljan Ring crater in Sweden, tilde 377 Ma, and others debated. The Hangenberg event at the Devonian Carboniferous boundary, tilde 359 Ma, was particularly abrupt, eliminating many remaining placoderms and conodont lineages and setting the stage for Carboniferous ecosystems dominated by different groups. By the end of the Devonian, the Earth had changed profoundly. Forests of tree-sized plants covered lowlands and river margins in tropical and subtropical belts. Soils were thicker and richer in organic matter. Atmospheric CO2 had begun a long decline, from several thousand ppm in the early Devonian toward 1,000–2,000 ppm by the Carboniferous Permian boundary, partly because of enhanced silicate weathering by plant roots and mycorrhizal fungi. Oxygen levels were rising toward their Paleozoic peak, possibly exceeding 30% PAL by the latest Devonian according to some COPS and GEOCARBSULF models. Tetrapods had taken their first steps onto land. Marine food webs, although battered by extinction, still supported diverse jawed fishes, early sharks, and recovering invertebrate communities. The fiery, anoxic, volcano-blanketed world of Earth's infancy was now a distant memory. The planet's volcanic engine had long been confined to narrow tectonic belts and deep mantle plumes. Its surface supported blue oceans, green landmasses, and breathing, crawling, eventually walking animals. The Devonian closed one chapter, the full establishment of complex life in water and the first successful excursions onto land, and opened the next. The lush, swampy, coal-forming world of the Carboniferous, when oxygen would reach some of its highest levels ever, giant arthropods would roam the forests, and tetrapods would begin to diversify into the lineages that would lead to amphibians, reptiles, mammals, and ultimately ourselves. We now cross into the Carboniferous period, 359 to 299 million years ago, the time when Earth came closer than it ever has before or since to resembling the lush, oxygen-drenched, forest-covered world that popular imagination sometimes projects onto the entire pre-human past. This is the age of coal forests, of towering lycopsid trees reaching 30-50 meters into a humid sky, of seed ferns carpeting the understory, of giant horsetails forming dense thickets along riverbanks and lake margins, and of atmospheric oxygen concentrations climbing to levels that, according to the most widely accepted geochemical models, reached between 30% and possibly as high as 35% of the present value, levels never again attained in Earth history. It is also the period when land animals diversified dramatically, when the first fully terrestrial vertebrates, the amniotes, appeared, when winged insects reached sizes never seen before or since, and when the long, slow burial of enormous volumes of plant matter set the stage for the coal seams that would later power the Industrial Revolution. By the opening of the Carboniferous, the Devonian extinctions had already culled many of the armored placoderm fishes and reef-building stromatoporoids, but the surviving lineages, especially the bony fishes and the early tetrapods, were poised for renewed expansion. The supercontinent assembly that would eventually produce Pangaea was well underway. Gondwana in the south, Laurentia plus Baltica plus Avalonia in the north, and various smaller blocks drifting toward collision zones. This tectonic convergence created vast, low-lying, tropical to subtropical coastal plains and epicontinental seas, ideal settings for the development of widespread swamp and wetland ecosystems that became the famous Carboniferous coal measures. The Mississippian subperiod, early Carboniferous, 359–323 Ma, is sometimes called the Age of Crinoids because echinoderms, particularly stalked crinoids, reached their all-time peak diversity and abundance, forming dense gardens on shallow carbonate platforms. Tabulate and rugose corals continued to build reefs, although less extensively than in the Ordovician and Silurian. Brachiopods, bryozoans, and fusulinid foraminifera, large, rice grain-sized protists with complex calcareous tests, proliferated in shallow marine environments. Sharks and early ray-finned fishes diversified further, while lobe-finned sarcopterygians gave rise to more advanced tetrapodomorphs. On land, however, the real transformation was botanical. Following the late Devonian evolution of archaeopterid trees and early seed plants, the Mississippian saw the rapid spread of lycopsid trees, Lepidodendron, Sigillaria, giants with thick, scale-covered trunks, shallow stigmarian root systems that spread laterally rather than deeply, and reproductive structures, strobili borne high in the canopy. These lycopsids grew extremely rapidly in the wet, nutrient-rich floodplains and deltaic environments created by rising sea levels and sediment input from eroding mountain belts, the Acadian Hercynian orogenies. Interspersed among them were calamitation sphenopsids, giant horsetails, pteridosperms, seed ferns such as metallosa with large fronds and seeds, and progymnosperms. The absence of deep-rooted gymnosperms and angiosperms meant that soils remained thin and waterlogged in many areas, perfect conditions for peat accumulation rather than complete decomposition. The most striking biological feature of the Carboniferous is the enormous size of terrestrial arthropods. Arthropleura, a millipede-like myriapod, reached lengths of 2.5 meters and widths of nearly half a meter. Meganeura and other griffinfly-like insects had wingspans up to 70–75 cm. Pulmonate arachnids and early scorpions also attained impressive dimensions. The standard explanation invokes the elevated atmospheric oxygen. Higher partial pressure of O2 allows diffusion-based respiration, tracheal systems in insects, book lungs in arachnids, to support larger body sizes without requiring more efficient circulatory systems. While oxygen was almost certainly a permissive factor, ecological opportunity, abundant plant litter, low competition from vertebrate herbivores, and reduced predation pressure in the understory likely played an equally important role. The Pennsylvanian sub-period, late Carboniferous, 323–299 Ma, marks the acme of the coal forests. Cyclic sedimentation patterns, cyclones, alternating coal, shale, sandstone, limestone, and underclay, record repeated glacial-interglacial cycles driven by Gondwanan ice ages. During low stands, swamps expanded across vast coastal plains. During high stands, marine transgressions drowned the peat mires and deposited limestones rich in brachiopods, crinoids, and fusulinids. These cycles, modulated by orbital forcing Milankovitch cycles, amplified by the large southern ice cap, produce some of the thickest and most laterally continuous coal seams in Earth history, seams that today stretch across much of the eastern United States, western Europe, and northern China. Tetrapods diversified markedly during the Pennsylvanian. Early forms were still largely amphibian-like labyrinthodonts with moist skin, external gills in larvae, and reproduction tied to water. But around the middle of the period, 310–305 Ma, the first amniotes appeared, small, lizard-like animals with the key innovation of the amniotic egg, a shelled egg with extraembryonic membranes, amnion, chorion, allantois, that allowed reproduction entirely on land without returning to water. This freed vertebrates from aquatic breeding sites and opened drier inland habitats. The earliest amniotes are divided into two lineages: synapsids, mammal-line reptiles, eventually leading to therapsids and mammals, sauropsids, reptile line, eventually leading to diapsids, lizards, dinosaurs, birds, and anapsids, turtles. Both groups were initially small, probably insectivorous or carnivorous, and lived in the litter and undergrowth of the coal forests. The oldest definitive amniote fossils come from the Joggins Formation in Nova Scotia, 315 Ma, a classic Coal Age lagerstet that preserves upright lycopsid stumps in life position, with small tetrapods preserved inside some of them, apparently having fallen into hollow trunks and become trapped. The coal forests also supported a rich invertebrate fauna: giant myriapods, cockroach-like dictyopterans, paleodictyopteroid insects with sucking mouthparts, possibly feeding on plant fluids or spores, and early web-spinning spiders. Vertebrate predators included large embolomer amphibians, crocodile-like aquatic forms, and the first large carnivorous amniotes toward the end of the period. Tectonically, the Carboniferous saw the final suturing of Laurasia with Gondwana along the Alleghenian-Variscan-Hercynian orogenic belt, forming the equatorial core of the future Pangaea. This mountain-building episode accelerated silicate weathering, helping draw down atmospheric CO2 from several thousand ppm in the early Carboniferous to perhaps 800–1500 ppm by the Permian boundary. The combination of massive carbon burial in peat coal and enhanced weathering produced a long-term cooling trend that intensified Gondwanan glaciation, especially in the late Pennsylvanian. By the close of the Carboniferous, 299 Ma, the Earth supported vast swampy equatorial coal forests with 30–50 m trees and giant arthropods, atmospheric oxygen at or near its Phanerozoic maximum. 35% PAL, fully terrestrial reproduction in amniotes, freeing vertebrates from water-diverse marine ecosystems still dominated by brachiopods, crinoids, fusulinids, and rugose corals, a planet whose volcanic activity was fully internalized, confined to subduction-related arcs, rift zones, and hot spots. With no trace remaining of the Hadean-style global lava seas, the stage was now set for the Permian, the final period of the Paleozoic, when the full assembly of Pangaea, the largest mass extinction in Earth history, and the rise of new ecosystem structures would once again reshape life on Earth. But that dramatic chapter belongs to the next phase of our story. We now enter the Permian period, 299 to 252 million years ago, the final chapter of the Paleozoic era, and one of the most climatically, geographically, and biologically dramatic intervals in the entire 4.6 billion year story of Earth. By this point, the planet had long since left behind the molten, globally volcanic hellscape of its Hadean youth. Volcanic activity had been fully channeled into the deep interior for billions of years. Eruptions occurred only where tectonic plates diverged at mid-ocean ridges, converged at subduction zones, or where mantle plumes punched through the lithosphere at hot spots. No longer did lava seas cover the surface. Instead, the mantle's slow convection sustained a mature rock cycle that recycled crust, regulated long-term climate through carbonate-silicate feedback, and delivered essential nutrients to surface ecosystems. The Earth that greeted the Permian was already oxygen-rich, biologically complex, and capable of supporting large terrestrial animals. Yet the Permian would push these conditions to extremes before inflicting the most severe biotic crisis ever recorded. The opening of the Permian coincides with the final welding together of all major continental blocks into the supercontinent Pangaea. Gondwana, the southern continents, collided with Laurussia along the Hercynian-Alleghenian suture, while Siberia and Angara docked from the north and various smaller terrains filled gaps in between. The result was a single landmass roughly C-shaped, stretching from pole to pole with an equatorial belt of vast coastal lowlands, an interior of increasingly arid desert and dry woodland and mountain ranges, the ancestral Appalachians, Urals, and Mauritanides, rising along the collision zones. This configuration created extreme continentality. The interior of Pangaea was far from oceanic moisture sources, producing some of the most severe seasonal temperature swings and aridity ever seen on Earth. In the early Permian Ciceralian, 299–273 Ma, the coal swamps that had dominated the late Carboniferous persisted in equatorial regions, especially along the margins of the newly formed supercontinent. Lycopsid trees, lepidodendron successors, calamites, seed ferns, and cordatelians, tall conifer-like trees with strap-shaped leaves, continued to form thick peat accumulations. But as Pangaea consolidated and mountain belts rose, rainfall patterns shifted. The vast interior began to dry out, and by the Middle Permian Guadalupean, 273–259 Ma, true coal formation had largely ceased in low latitudes. Instead, drier adapted floras took over. Conifers, Walkian voltzaelians with needle-like leaves and winged seeds, glossopterids, southern hemisphere tongue-shaped leaves that became emblematic of Gondwanan glaciation evidence, and peltosperms, another seed fern group. These plants were better suited to seasonal drought and lower groundwater tables. The southern high latitudes remained under the influence of the waning Karoo-Gondwana ice sheet. Glacial deposits, striated pavements, and dropstones are found across southern Africa, Antarctica, India, Australia, and South America, the classic evidence Alfred Wegener used to support continental drift. As the Permian progressed, the ice cap retreated, leaving behind post-glacial lakes and fluvial systems rich in organic matter. On land, vertebrate life underwent one of its most important transitions. The synapsid mammal line amniotes, which had appeared modestly in the Carboniferous, radiated explosively in the Permian. The pelycosaurs, most famously Dimetrodon with its tall neural spine sail, dominated early Permian faunas in equatorial North America and Europe. These sail-backed predators and herbivores cassades were ectothermic or at best inertial homeotherms. By the Middle Permian, the more advanced therapsids, mammal-like reptiles, replaced them. Therapsids show numerous features converging on mammalian biology. More upright posture and more efficient limb mechanics, enlarged temporal fenestrae, housing larger jaw-closing muscles, differentiation of teeth into incisors, canines and post-canines, early heterodonty, secondary palate, allowing simultaneous breathing and chewing evidence in some lineages, cynodonts of hair, whiskers, and possibly endothermy, the dinosaurians, large, heavily built herbivores and carnivores, anomodonts, especially the beaked dicynodonts that would survive into the Triassic. Gorgonopsians, saber-toothed predators, and the Rosphalians, smaller, weasel-like forms, filled most large terrestrial predator and herbivore niches. By the late Permian Lopingian, 259–252 Ma, the cynodonts, direct ancestors of mammals, were already present as small, agile, likely nocturnal insectivores or omnivores. Diapsid reptiles leading to lizards, crocodilians, dinosaurs, and birds remained less diverse but were ecologically important, especially in drier regions. Parareptiles, including the periasaurs, large, armored herbivores, and early archosauromorphs also occupied niches. Amphibians persisted in wetter habitats but were increasingly marginalized as aridity spread. Marine ecosystems in the Permian were dominated by brachiopods, especially productids with spines and rich internal structures, fusulinid foraminifera reaching soccer ball sizes in some species, ammonoids, bryozoans, and rugose corals, though reefs were less extensive than earlier. Crinoids and blastoids remained abundant. The first scleractinian corals appeared late in the period, although they would not become major reef builders until the Triassic. Sharks, ray-finned fishes, and coelacanths continued to diversify. The most dramatic event of the Permian and the defining punctuation mark of the entire Paleozoic is the end Permian mass extinction, the greatest biotic crisis in Earth history. At Ma, over 200,000 years, roughly 81–96% of all marine species and percent of terrestrial vertebrate species disappeared. Entire groups vanished. Rugose and tabulate corals, blastoids, productid brachiopods, most fusulinids, trilobites, finally extinct after 270 million years, and many ammonoid lineages. On land, Gorgonopsians, Dinosaurians, most the Rosphalians, and many parareptiles disappeared. Only a handful of therapsid lineages, especially small cynodonts and dicynodonts, and some archosauromorphs survived into the Triassic. The primary trigger is now widely accepted to be the eruption of the Siberian Traps, one of the largest large igneous provinces ever formed. Between ~252, 0 and ~251, 4 Ma, ~34 million cubic kilometers of basalt and associated explosive volcanism poured out across what is now Siberia. This relates tens of thousands of gigatons of CO2 right arrow extreme global warming, 5–10 degrees C or more massive SO2 and halogen emissions, acid rain and ozone depletion, methane clathrate destabilization, right arrow additional greenhouse forcing toxic metal loading, mercury, etc. Into oceans and soils, the warming caused widespread marine anoxia/euxinia, hydrogen sulfide-rich bottom waters, killing off aerobic organisms and allowing anaerobic microbes to dominate. Oceanic pH dropped, hypercapnia and ocean acidification, dissolving carbonate shells. On land, increased aridity, acid rain, and wildfire frequency devastated forests and soils. The recovery in the early Triassic was painfully slow. The Triassic recovery interval lasted 5–10 million years before diversity began to rebound significantly. Early Triassic ecosystems were low diversity, with disaster taxa Lystrosaurus, a dicynodont that became globally abundant, and the generalist bivalve Claria dominating. Marine food webs were simple. On land, small cynodonts, procolophonids, and early archosauromorphs eked out a living in a greenhouse world with monsoonal climates and widespread red beds indicating oxidized, poorly vegetated landscapes. By the end of the Permian, the Earth had reached the zenith of Paleozoic habitability, lush equatorial forests, towering synapsids, giant amphibians in wet refugia, diverse marine reefs, only to suffer a near-total reset. The volcanoes, long since confined to tectonic margins and mantle plumes, delivered one final, cataclysmic pulse that nearly erased complex life. Yet life endured. The survivors' small, generalist, burrowing or aquatic forms would repopulate a warmer, more oxygen-poor early Triassic world and set the stage for the Mesozoic era, the age of reptiles, and eventually the dinosaurs. We emerge now from the shadow of the greatest mass extinction ever recorded, stepping into the Triassic period, 252 to 201 million years ago, the opening act of the Mesozoic era, often called the Age of Reptiles. At the dawn of the Triassic, the Earth was a wounded world. The Siberian Traps eruptions had released enough greenhouse gases, sulfur compounds, toxic metals, and heat to drive global temperatures up by at least 610 degrees C, perhaps more in some spikes, collapse nearly every major marine ecosystem, and reduce terrestrial vertebrate diversity to a handful of resilient lineages. Atmospheric oxygen had fallen sharply during the crisis. Some models place it as low as 12–16% of present levels in the earliest Triassic, while carbon dioxide soared into the thousands of parts per million. The single landmass of Pangaea sat almost symmetrically astride the equator, its vast interior a hyper-arid megamonsoon, desert ringed by narrow, humid coastal belts where the last pockets of late Permian forests had barely clung on. Yet even in this scorched, low-oxygen, high CO2 aftermath, life did not surrender. The recovery that unfolded over the next 10 million years, painfully slow by geological standards, set the stage for one of the most important ecological reorganizations in Earth history, the rise to dominance of the Archosaurian reptiles and the first appearance of true dinosaurs. In the early Triassic, Induan and Olnikian stages, 252–247 Ma, the biosphere was dominated by a tiny number of disaster taxa. On land, the herbivorous Dicynodont Lystrosaurus became extraordinarily abundant, sometimes comprising 90–95% of all vertebrate individuals in fossil assemblages from South Africa, Antarctica, Russia, and China. This pig-sized, beaked, burrowing synapsid was pre-adapted for low oxygen, high CO2 conditions, barrel chest, efficient lungs, possibly some capacity for nasal glands to excrete excess salt, and the ability to estivate in burrows during the harshest dry seasons. Alongside it survived small, opportunistic cynodonts, the direct ancestors of mammals, procolophonid parareptiles, squat, lizard-like herbivores with beak-like jaws, and a few early archosauromorphs, slender, long-limbed reptiles already showing the characteristic ankle structure, metatarsal joint, that would later define archosaurs. Marine recovery was even slower. The oceans remained stratified and euxinic in many basins for several million years. The dominant survivors were generalist bivalves, Claria, Unionites, small gastropods, and the Inozoan sponge-like disaster taxa that could tolerate low oxygen. Reef ecosystems were absent, the last rugose and tabulate corals were gone forever. Ammonoids radiated quickly from a few surviving genera, but overall diversity remained depressed until the late early Triassic Spathian substage, tilde 248–247 Ma, when oxygen began to rebound and carbonate platforms started to reform. Volcanism during the early Triassic was comparatively subdued compared with the cataclysmic Siberian traps, but smaller-scale large igneous activity continued in places, e.g., the tilde 251–248 Ma Angara Vilui province remnants. These eruptions, together with ongoing release of methane from destabilized seafloor clathrates and permafrost, helped maintain the greenhouse state. Pangaea's configuration amplified seasonal extremes. Powerful monsoonal circulation brought torrential wet season rains to the coasts and equatorial interior lakes, followed by months of scorching drought. Red bed sediments, oxidized siltstones and sandstones dominate continental successions, reflecting well-aerated but sparsely vegetated landscapes. By the Middle Triassic, Anisian and Ladinian stages, 247–237 Ma, conditions began to improve markedly. Oxygen levels climbed back toward 18–22% PAL according to COPS and GEOCRBSULFOR models. Carbon dioxide remained high 1,2500 ppm, sustaining a warm, ice-free climate with average global temperatures till to 36 degrees C above modern values. Vegetation recovered. The conifer-dominated Voltzian flora of the early Triassic gave way to more diverse forests of Voltzian conifers, cycadoids, ginkgophytes, ferns, and the first bennettitales, cycad-like plants with flower-like reproductive structures. In Gondwana, the seed fern Dicroidium formed widespread woodlands. Archosaurian reptiles now took center stage. Two major clades diverged early: Pseudosuchia, crocodile-line archosaurs; Edosaurs, armored herbivores; Roysuchians, large-headed carnivores with pillar-erect posture; and Phytosaurs, crocodile-like ambush predators with elongate snouts. Avametidarsalia, bird-line archosaurs or ornithodorans; Ladrupedids, salsaurids, early dinosaur-like herbivores; pterosaurs, the first flying vertebrates, appearing by 228–225 Ma in the late Triassic, and crucially, dinosaurs themselves. The oldest generally accepted dinosaur body fossils appear in the late Carnian, 233–232 Ma, early late Triassic. Aeoraptor, Herrerasaurus, Piscinosaurus, and others from the Ischigualasto Formation of Argentina and equivalent beds in Brazil. Trackways from slightly older strata, 235 Ma in Poland, Italy, and the American Southwest already show unmistakable dinosaurian footprints, tridactyl, digitigrade with narrow heel impressions. Dinosaurs were initially small to medium-sized, 1–4 m long, bipedal or facultatively quadrupedal, and ecologically marginal compared with the larger Roysuchians and Phytosaurs. What set them apart and ultimately allowed their dominance was a suite of anatomical advantages. Fully erect limb posture with parasagittal gait, more efficient than the sprawling or semi-erect postures of most other reptiles; advanced ankle structure allowing faster, more stable running air sac respiratory system, inferred from pneumatic vertebrae in the earliest forms. Shared with later birds and pterosaurs, possibly higher metabolic rates and partial or incipient endothermy even in basal members during the Carnian stage, 237–227 Ma, a major climate perturbation known as the Carnian Pluvial Event, CPE, linked to volcanic activity in the Rangelia Large Igneous Province and possibly other circum-Pangaean eruptions, brought a several million-year interval of increased humidity and rainfall across much of Pangaea. Lakes and rivers expanded, coal formation briefly resumed in some regions, and conifer forests were replaced by more diverse fern-dominated vegetation. This wet phase appears to have stressed many pseudosuchian lineages while favoring more adaptable, smaller, faster-growing dinosaurs and pterosaurs. By the end of the Carnian, many of the large Roysuchians and Edosaurs had declined sharply. The Norian and Rhaetian stages, late Triassic, 227–201 Ma, mark the true takeover. Dinosaurs radiated into multiple lineages. Sauropodomorphs, early prosauropods such as Plateosaurus and Rheogosaurus, some already reaching 8–10 m and several tons; theropods, Coelophysis and kin; small to medium agile predators, ornithischians; early armored forms such as Scutelosaurus, Heterodontosaurids, and basal thyreophorans. Phytosaurs, Edosaurs, and Roysuchians remained abundant but were increasingly ecologically displaced. Pterosaurs diversified into long-tailed rhamphorhynchoids and early short-tailed pterodactyloids. On land, small mammals, docodonts, harameodons, morganeucodontids, remained shrew to rat-sized, nocturnal, and insectivorous, living in the undergrowth. Marine ecosystems finally recovered to near pre-extinction diversity. Scleractinian corals, modern-style reef builders, appeared and began constructing patch reefs. Ichthyosaurs and nothosaurs radiated into dolphin and seal like marine reptiles. Plesiosaurs appeared late in the period. Conodonts, the last survivors of the Conodontophorids, finally went extinct at the Triassic-Jurassic boundary. The Triassic ended with another extinction pulse at tilde 201, 4 the Triassic-Jurassic mass extinction, linked to the Central Atlantic Magmatic Province, CAMP, one of the largest large igneous events ever, associated with the initial rifting of Pangaea and the opening of the Atlantic Ocean. CO2 release drove another tilde 48 degrees C warming spike, ocean acidification, and widespread anoxia. Non-avian dinosaurs, pterosaurs, many marine reptiles, and numerous terrestrial plants survived. Most pseudosuchians, phytosaurs, and several marine groups did not. By the close of the Triassic, the groundwork for the Jurassic world was laid. Dinosaurs had become the dominant large terrestrial vertebrates. The first true mammals were present but marginal. Flying reptiles had taken to the skies. Coral reefs were re-established. Pangaea had begun to split, heralding new ocean circulation patterns and climate moderation. And the volcanic forces that had once blanketed the planet in lava were now, as they had been for billions of years, confined to rift zones, subduction arcs, and mantle hotspots, quietly sustaining the long-term geochemical cycles that kept Earth habitable. The Mesozoic proper, the age of dinosaurs, was about to begin in earnest. We now plunge into the Jurassic period, 201 to 145 million years ago, often romanticized as the golden age of dinosaurs, a time when these remarkable reptiles reached their first peak of diversity, size, and ecological dominance across a warming, fragmenting supercontinent. The Triassic-Jurassic mass extinction had cleared the board. Most non-dinosaurian archosaurs, phytosaurs, roysuchians, etosaurs were gone, as were many marine invertebrates and several plant groups. The survivors, especially the dinosaurs, pterosaurs, and marine reptiles, inherited a world still recovering from the Central Atlantic Magmatic Province eruptions, with atmospheric carbon dioxide elevated, likely 1,000–2,000 ppm or higher in the early Jurassic, oxygen rebounding toward 20–25% of present levels, and a greenhouse climate with no polar ice caps and global average temperatures tilde 5–7 degrees C above modern values. The early Jurassic Hadean to Tortian stages, 201–174 Ma, is marked by a continued recovery from the end Triassic crisis. Pangaea began to rift more actively along the North Atlantic margins, with volcanic activity in the Karoo-Ferrar Large Igneous Province, tilde 183 Ma, and ongoing camp aftershocks contributing to short-term warming and anoxia events. The most notable is the Tortian Oceanic Anoxic Event, TOA, tilde 183 Ma, a global perturbation characterized by widespread black shale deposition, positive carbon isotope excursions indicating massive organic carbon burial, and a minor extinction among marine invertebrates, ammonites, brachiopods, bivalves, and some terrestrial plants. This event, likely triggered by Karoo volcanism releasing CO2 and methane, briefly intensified the greenhouse and caused ocean deoxygenation, but it also fertilized the seas with nutrients, boosting primary productivity. On land, dinosaurs solidified their rule. Sauropodomorphs, the long-necked herbivores, evolved into true giants. Early sauropods like Vulcanodon, tilde 190 Ma, Zimbabwe, and Barapasaurus, tilde 183 Ma, India, reached 12–15 m in length with columnar limbs, elongated necks, and simple chisel-like teeth suited for stripping foliage. These were the precursors to the Jurassic titans. Theropods diversified into coelurosaurians, small, agile forms leading to birds, ceratosaurs, abelisaurus kin, and tetanurans, including allosaurids and megalosaurids. Ornithischians remained less common but included early thyreophorans, armored dinosaurs like Celidosaurus, and heterodontosaurids, small, beaked herbivores. Vegetation shifted toward a more modern aspect. Conifer forests, araucarians, podocarps, cheropodids with scale-like leaves adapted to dry conditions, dominated drier interiors, while ferns, cycads, and bennettitilians formed lush understories in what are coastal and riverine areas. The first unequivocal evidence of flowering plants, angiosperms, is debated for the late Jurassic or early Cretaceous, but molecular clocks suggest their cryptic origins may trace back here. Insect diversity exploded with the first bees, ants, and termites appearing, pollinating gymnosperms and shaping early co-evolutionary relationships. In the oceans, marine reptiles radiated spectacularly. Ichthyosaurs evolved tuna-like bodies with vertical tail, fins, and viviparity, live birth, reaching lengths up to 15 m, e.g., Temnodontosaurus. Plesiosaurs diversified into long-necked, small-headed forms, elasmosaurids, and short-necked, large-headed pliosaurs like Leopleurodon, though actually middle-late Jurassic. Thalidosuchians, crocodile-like marine crocodilomorphs, filled niches from shallow water ambush predators to fully pelagic forms with flippers and fish-like tails. Ammonites rebounded with intricate suture patterns and diverse shell shapes, serving as key index fossils. Scleractinian corals began building more extensive reefs, hosting diverse fish, bivalves, and gastropods. The Middle Jurassic, Alenian to Caluvian stages, 174–164 ma, saw Pangaea's breakup accelerate, with the central Atlantic Ocean widening and the Gulf of Mexico opening. This rifting moderated the extreme continental climate, increasing humidity and reducing megamonsoon intensity. Sea levels rose, flooding continental margins and creating extensive shallow epicontinental seas like the Sundance Sea in western North America. Dinosaur faunas reached new heights. In China's Dashenpu Formation, ~167 ma, we find early Mamenchisaurids, sauropods with extraordinarily long necks, up to 9 m in Mamenchisaurus. In Europe and Africa, megalosaurid theropods like Eustreptospondylus preyed on stegosaurs, early plated dinosaurs such as Huyangosaurus. North America's Morrison Formation precursors hint at the coming late Jurassic bonanza. Pterosaurs diversified. Rhamphorhynchoids with long tails and toothed jaws shared the skies with early pterodactyloids, short-tailed, often toothless forms like Pterodactylus. Mammals remained small and nocturnal, but diversified into multituberculates, rodent-like with complex molars for grinding, docodonts omnivorous with shearing teeth, and triconodonts carnivorous with piercing cusps. The first gliding mammals, Volaticotherium, and swimming forms, Castorocauda, appeared, showing early ecological experimentation. The late Jurassic Oxfordian to Tithonian stages, 164–145 ma, is the iconic Jurassic Park era, epitomized by the Morrison Formation in the western United States, ~155–148 ma. Here sauropods achieved colossal sizes. Diplodocus up to 25 m, 10–15 tons, Brachiosaurus 26 m, 40–50 tons, and Apatosaurus 21 m, 20–30 tons browsed on conifers and ferns using peg-like teeth and gastroliths for grinding. Their anatomy, hollow vertebrae, air sacs, efficient one-way lung flow, allowed such gigantism under Jurassic oxygen levels. Theropods included Allosaurus 9 m, a pack-hunting apex predator with serrated teeth and powerful jaws, and smaller coelurosaurs. Stegosaurs, Stegosaurus with its plated back and spiked tail, and ankylosaurs, early nodosaurids, defended against them. Ornithopods like Camptosaurus foreshadowed later duck bills. In Tanzania's Tendaguru Formation, ~155–150 ma, similar faunas with Jurafatitan, a brachiosaurid, and Kentrosaurus, a stegosaur, show Gondwanan connections. Portugal's Lourinhã Formation reveals Torvosaurus, one of the largest theropods at 10 m. Pterosaurs peaked in diversity. Pteranodon precursors and Ajdarchid-like forms soared over seas and lands. The first birds appeared, Archaeopteryx ~150 ma, from Germany's Solnhofen limestone, A crow-sized theropod with feathers, asymmetrical flight quills, a long bony tail, and toothed jaws represents the transition from non-avian dinosaurs to avians. Multiple specimens show it was a glider or weak flyer, perching in trees and catching insects or small prey. Marine realms thrived. Pliosaurs like Pleiosaurus reached 12 m with massive skulls and conical teeth for crushing ammonites and ichthyosaurs. Belemnites, squid-like cephalopods with internal guards, proliferated. Coral reefs expanded in the Tethys Sea, supporting diverse echinoids, crinoids, and teleost fishes. By the end of the Jurassic, the Atlantic was a young ocean. South America and Africa were beginning to separate, and India was drifting northward. Sea levels were high, climates mild, and dinosaurs ruled unchallenged. Volcanism remained confined to rift zones and subduction arcs, with no major large igneous provinces disrupting the stability. Oxygen hovered around 22–25% PAL. CO2 declined slightly toward 800–1500 ppm as weathering increased with rifting. The Jurassic closed with a minor extinction at the Tithonian Berriasian boundary, ~145 Ma, affecting some ammonites and stegosaurs, but it was mild compared to what awaited in the Cretaceous. The stage was set for the final Mesozoic act, the rise of flowering plants, the evolution of tyrannosaurs and hadrosaurs, the first true birds and modern mammals, and the cataclysmic end of the non-avian dinosaurs. We now transition into the Cretaceous period, 145 to 66 million years ago, the final and arguably the most vibrant chapter of the Mesozoic era, a time when Earth's habitability for animals reached unprecedented heights. By this era, the planet had fully evolved from its primordial fiery rock state, with volcanoes long confined to the depths, their activity internalized through plate tectonics. The mantle's convection currents drove subduction zones where oceanic crust plunged back into the interior, recycling materials and sustaining the carbon cycle that kept the atmosphere balanced. No trace remained of the Hadean lava oceans. Instead, eruptions were localized at arcs like the Andes precursors or hotspots like the Deccan traps, which would play a role later. Oxygen levels stabilized around 22–28% of present atmospheric values, higher than today, supporting massive body sizes and active metabolisms. Carbon dioxide hovered between 500–1500 ppm, creating a hothouse climate with average global temperatures 4–8 degrees C warmer than now, no permanent ice caps, and sea levels up to 200 meters higher, flooding continents with shallow seas teeming with life. The early Cretaceous Berriasian to Albian stages, 145–100 Ma, began with the continued rifting of Pangaea. The South Atlantic Ocean opened as South America and Africa pulled apart. India accelerated northward toward Eurasia, and the Tethys Sea narrowed. This tectonic reconfiguration increased volcanic activity along new rifts and subduction zones, releasing CO2 that amplified the greenhouse effect but also enhanced weathering, drawing down some carbon over time. Shallow epicontinental seas expanded, such as the Western Interior Seaway in North America, creating vast, warm, nutrient-rich habitats for marine animals. Dinosaurs dominated terrestrial ecosystems, building on Jurassic foundations. Sauropods continued their gigantism. Argentinosaurus from Argentina, Ma, may have reached 30–35 meters and 7,100 tons, with a long neck for high browsing and a massive gut for fermenting vegetation. Titanosaurs like Patagotitan emerged, with some estimates suggesting even larger sizes, supported by efficient air sac lungs and lightweight pneumatic bones. Theropods diversified. Tyrannosauroids like Uteranus ~125 Ma, China, showed feather-like filaments, hinting at insulation or display in cooler climates. Carcharodontosaurids Giganotosaurus ~98 Ma, Argentina, rivaled tyrannosaurs in size with blade-like teeth for slashing flesh. Ornithischians radiated. Hadrosaurids, duck-billed dinosaurs, appeared with complex dental batteries for grinding plants, while ceratopsians, horned dinosaurs like Psittacosaurus, began as small bipeds. A revolutionary botanical shift occurred. The the rise of angiosperms, flowering plants. First unambiguous fossils appear in the early Cretaceous, 135–125 Ma, from China and Europe, simple leaves and pollen grains. By the Permian Aptian, 130–113 Ma, they diversified rapidly, evolving flowers, fruits, and symbiotic relationships with insects. This Cretaceous terrestrial revolution transformed landscapes. Ferns and gymnosperms gave way to angiosperm-dominated forests, increasing primary productivity, accelerating soil formation, and providing new food sources. Herbivorous dinosaurs adapted, with hadrosaurs developing broad muzzles for cropping low vegetation. Marine life flourished. Mosasaurs, giant marine lizards up to 17 meters, Mosasaurus, evolved from varanoid ancestors with streamlined bodies, paddle limbs, and powerful jaws for ambushing fish and ammonites. Plesiosaurs peaked. Elasmosaurids like Albertonix had necks up to 7 meters with 76 vertebrae, snaking through water to snap at prey. Ichthyosaurs declined but persisted as fast swimmers. Sharks like Cretaceous, the Jinsu shark, grew to 7 meters with serrated teeth. Teleost fishes exploded in diversity, forming schools in shallow seas. Ammonites evolved baroque shell shapes with complex sutures for buoyancy control. Rudist bivalves built massive reef-like structures, rivaling corals in tropical shallows. Pterosaurs reached their zenith. Azhdarchids like Quetzalcoatlus, 68 Ma, but precursors in early Cretaceous, had wingspans up to 10–12 meters, possibly the largest flying animals ever, stalking prey on long legs like giant storks. Nyctosaurids developed elaborate crests for display. Mammals, still small, diversified subtly. Multituberculates like Cryptobotter had rodent-like incisors. Metatherians, marsupial ancestors, and eutherians, placental ancestors, appeared by Ma. They occupied niches as burrowers, climbers, and gliders, avoiding dinosaur competition. The mid-Cretaceous Cenomanian to Turonian stages, 189 Ma, marked the Cretaceous thermal maximum, with temperatures peaking at 10–15 degrees C above modern, driven by high CO2 from volcanic provinces like the Caribbean Large Igneous Province. Oceanic anoxic events, OAEs, like OAE2–94 Ma, caused widespread black shale deposition as algal blooms depleted oxygen, stressing marine life but burying carbon to eventually cool the climate. Terrestrial faunas shifted regionally. In Asia, tyrannosaurids like Tarbosaurus emerged as apex predators. In North America, the dinosaur park formation precursors showed diverse assemblages. Ankylosaurids, Euoplocephalus with clubbed tails, Pachycephalosaurids, dome-headed rammers, and early tyrannosaurids. Gondwanan isolation fostered unique forms. Abelisaurids, Majungasaurus, 70 Ma, Madagascar with short snouts and vestigial arms. Spinosaurids, Spinosaurus, 95 Ma, North Africa, with sail backs and crocodile-like jaws for fish eating. Birds diversified from Archaeopteryx descendants. Enantiornithines, opposite birds, dominated with toothed beaks and clawed wings. Ornithuromorphs, leading to modern birds, developed stronger flight. Confuciusornis, 125 Ma, China, formed flocks with long tail feathers for display. The late Cretaceous Coniacian to Maastrichtian stages, 89–66 Ma, saw cooling trends as CO2 declined through enhanced weathering and carbon burial. Sea levels remained high, but continents approached modern configurations. India collided with Asia, 50 Ma, but rifting accelerated in Cretaceous. Antarctica separated from Australia, initiating circumpolar currents. Dinosaur diversity peaked. In North America, the Hell Creek Formation, 68–66 Ma, epitomized. Tyrannosaurus rex, 12 m, 7 tons with bone-crushing bite force up to 57,000 N. Triceratops with 3 horns and frilled skull for defense display. Edmontosaurus hadrosaur, herds migrating seasonally. Ankylosaurus wielded armored bodies and tail clubs. In South America, titanosaurs like Dreadnoughtus, 85 Ma, pushed size limits. In Mongolia, Velociraptor ~75 ma hunted in packs with sickle claws, Oviraptor brooded eggs. Marine megafauna thrived, mosasaurs like Tylosaurus patrolled oceans, ammonites like baculites grew straight shells up to 2 meters. Plesiosaurs persisted until the end. Insects co-evolved with angiosperms, butterflies, moths, and advanced bees appeared pollinating flowers. Social insects like ants formed colonies. The period ended catastrophically with the Cretaceous-Paleogene (KPG) extinction at ~66 ma. A 10-15 km asteroid struck Chicxulub, Mexico, vaporizing rock, triggering tsunamis, wildfires, and an impact winter from dust aerosols blocking sunlight. Concurrent Deccan traps eruptions ~66. 565.5 ma released km3 of lava, CO2, and sulfur, exacerbating warming acidification before the impact's cooling. Percent of species vanished, all non-avian dinosaurs, pterosaurs, mosasaurs, plesiosaurs, most ammonites, rudists. Survivors, small mammals, birds, crocodilians, turtles, lizards, amphibians, sharks, ray-finned fishes, angiosperms. The KPG reset opened the Cenozoic for mammals, yet the Cretaceous showcased Earth's peak Mesozoic habitability, diverse, giant animals in lush, warm ecosystems, sustained by internalized volcanic processes and a balanced atmosphere. The fiery origins were forgotten, replaced by a world alive with roars, flights, and swims until the sky fell. As the dust settled from the cataclysmic asteroid impact at Chicxulub and the lingering effects of the Deccan Traps volcanism faded, the Earth entered a new era, the Paleogene period, spanning from 66 to 23 million years ago. This was the dawn of the Cenozoic, often dubbed the Age of Mammals, where the survivors of the KPG extinction, small, adaptable creatures that had eked out an existence in the shadows of dinosaurs, finally stepped into the ecological spotlight. The planet, already far removed from its Hadean origins as a fiery, lava-shrouded rock with ubiquitous volcanoes spewing across a molten surface, had its volcanic forces long internalized. The mantle's convection now drove discrete eruptions at plate boundaries and hotspots, recycling the crust and maintaining the atmospheric balance that made life possible. Oxygen levels, which had dipped slightly during the extinction crisis, began a gradual recovery toward modern values around 18-21% of present atmospheric levels. Carbon dioxide, elevated in the immediate aftermath to perhaps 1,000–2,000 ppm, started a long decline as new forests expanded and weathering rates increased, cooling the climate from the Cretaceous hothouse toward more temperate conditions. The earliest Paleogene, the Paleocene epoch, 66–56 million years ago, was a time of recovery and reorganization. The impact winter caused by sulfate aerosols and dust blocking sunlight had plunged global temperatures by 5–10 degrees C for years or even decades, leading to acid rain, wildfires, and ecosystem collapse. But as the skies cleared, a greenhouse rebound from released CO2 and methane pushed temperatures back up, creating a warm, wet world with average global values around 12–15 degrees C higher than today in some intervals. Sea levels rose as the last remnants of the western interior seaway drained, and continents continued their drift. North America and Eurasia connected via Beringia, South America remained isolated, India collided with Asia around 50–55 million years ago, though the main uplift of the Himalayas accelerated later, and Australia drifted northward. Vegetation rebounded quickly. Ferns and conifers dominated early Paleocene landscapes, but angiosperms, already diverse in the late Cretaceous, exploded in variety, forming dense, multi-layered forests. In the northern hemisphere, broad-leaved deciduous trees like dawn redwoods, metasequoia, and early maples spread across Eurasia and North America. Tropical rainforests expanded in low latitudes, fueled by high humidity and no frost lines, even at high latitudes. These forests sequestered massive amounts of carbon, helping stabilize the climate and providing niches for emerging faunas. Mammals, freed from dinosaurian competition, underwent one of the most rapid adaptive radiations in evolutionary history. The three major living groups, monotremes, egg-laying like platypus, marsupials pouched like kangaroos, and placentals, uterine development like most modern mammals, had all diverged by the late Cretaceous, but Paleocene forms were mostly small, generalized omnivores or insectivores weighing under 1 kg. Archaic groups like multituberculates, rodent-like with complex molars, persisted, but placentals began to dominate. Early ungulate-like mammals, such as Protungulatum, scampered through undergrowth, with hooves precursor to later herbivores. Carnivorous creodonts like Arctocene and Mesonychids, hoofed predators resembling wolves, filled predator niches. Primates appeared early. Plesiadapes ma, North America and Europe, was a squirrel-like tree dweller with grasping hands and forward-facing eyes, hinting at the lineage leading to humans. In the oceans, the extinction had wiped out ammonites, belemnites, rudists, and most marine reptiles, but teleost fishes, sharks, and rays survived and diversified. Early whales, archaeocetes, evolved from even-toed ungulate ancestors around 5550 ma. Pakistus ~50 ma, Pakistan, was a wolf-sized, semi-aquatic carnivore with limbs adapted for wading, marking the transition from land to sea. Coral reefs recovered slowly, with scleractinians rebuilding complex structures in warm, shallow waters. Birds, the only dinosaur survivors, radiated explosively. Giant flightless forms like Gastornis, ~56 ma, Europe and North America, stood 2 meters tall, with massive beaks possibly for cracking nuts or small prey. Debate rages on whether they were carnivorous or herbivorous. Early anseriforms, ducks and kin, and galliforms, chickens, appeared, while seabirds like early pelicans colonized coasts. The Eocene epoch, 56-34 million years ago, brought the Cenozoic's thermal peak, the Eocene climatic optimum eco, ~5349 ma, with global averages up to 12 degrees C warmer than today, polar forests of temperate trees, and crocodiles in Arctic latitudes. This hothouse was driven by high CO2 1000-2000 ppm from volcanic outgassing in the North Atlantic igneous province, Ma, associated with Greenland-Norway rifting. Palm trees grew in Alaska, and rainforests blanketed much of the globe, enhancing biodiversity. Mammalian giants emerged. Indricotherium paraceratherium, 23 ma but Eocene precursors, was the largest land mammal ever, at 5 meters tall and 15-20 tons, a hornless rhino browsing on tree tops. Uintathers like Uintatherium, ~50 ma, sported bizarre skull knobs and tusks. Brontotheres, megasaurops, resembled rhinos with Y-shaped horns. Whales fully aquaticized, Ambulocetus, ~49 ma, swam with undulating spine and webbed feet. Basilosaurus, ~40 ma, reached 18 meters with vestigial hind limbs, fully marine but still serpentine. Primates diversified. Adapids like Notharctus, ~50 ma, were lemur-like with long tails. Ammomids tetonius were tarsier like nocturnal leapers. The first anthropoids, human monkey-ape ancestors, appeared in Asia around 45 ma, small and arboreal. Rodents exploded. Early squirrels, beavers, and mice-like forms colonized niches. Bats Icheronecterus, ~52 ma, already had echolocation. Sirenians, sea cows, and proboscideans, elephant kin, diverged. Miratherium, ~37 ma, was a pig-sized, semi-aquatic herbivore with incipient tusks. Birds included terror birds precursors and giant penguins like Anthropornis, ~40 ma, up to 1.7 meters tall in Antarctic waters. Reptiles survived. Crocodilians, turtles, and lizards adapted to the warmth. The Oligocene epoch, 34-23 million years ago, marked a shift to cooler, drier conditions. The Eocene-Oligocene transition, ~34 ma, saw a ~5 sea drop, driven by Antarctic ice sheet formation as Australia drifted north, opening the Drake Passage and initiating the Antarctic circumpolar current, isolating the continent and allowing glaciation. CO2 fell below 750 ppm, enhancing cooling. Sea levels dropped, exposing land bridges. Faunas modernized. In North America, oreodonts, sheep like artiodactyls, and camels, protolopus, appeared. Entelodonts, diod, and hell pigs were omnivorous giants with powerful jaws. In Asia and Europe, early rhinoceroses and tapirs diversified. Carnivorans split, caniforms, dogs, bears, and feliforms, cats, hyenas. Nimravids, false saber-tooths, hunted. South America isolated, developed unique marsupials. Sparassodonts, thylacosmolus precursors, saber-toothed predators, and giant ground sloths, early megatheriids. Australia saw early kangaroos and wombats. Oceans cooled, kelp forests emerged, supporting otters and seals. Whales diversified into odontocetes, toothed, like dolphins, and mysticetes, baleen, filter feeders. By Paleogene's end, mammals had claimed every major niche: flyers, bats, swimmers, whales, sirenians, burrowers, rodents, climbers, primates, and giants, indracotheres. The stage was set for the Neogene, with further cooling, grassland expansion, and hominid emergence. The Neogene period, 23.6 million years ago, saw the world inch toward modernity. The Miocene epoch, 23.5 Ma, began warm, the mid-Miocene climatic optimum, 1715 Ma, with Co 2-400-500 ppm and temperatures 3-4 degrees C above today. Forests dominated, but as Co 2 declined and continents uplifted, Himalayas, Andes, drier conditions spread. Grasslands expanded, driven by C4 photosynthesis evolution, 20 Ma, allowing efficient growth in hot, dry areas. This grassland revolution transformed herbivore evolution. Horses from three-toed to one-toed like Pleiohippus, camels, and antelopes developed high-crowned teeth for abrasive grasses. Apes radiated, proconsul 20 Ma Africa was tailless, arboreal, Dryopithecus, Ma Europe swung through trees. The great ape-human split occurred 7 Ma. Elephants diversified, Gomphotherium with 4 tusks, Dinotherium with downward curving tusks. Mastodons spread globally. Carnivores modernized, true saber-tooths, Smilodon precursors, bears, ursavis, and hyenas. South America's Great American Biotic Interchange began 3 Ma with Panama Isthmus rise, but Miocene precursors allowed some migration. Oceans, Megalodon, Carcharocles Megalodon, 23.6 Ma, ruled as 18-meter super shark preying on whales. The Pliocene epoch, 5.32.6 Ma, cooled further, with northern hemisphere glaciation precursors. Sea levels fluctuated, Mediterranean dried during Messinian salinity crisis, 6 Ma, forming salt deposits. Hominids emerged, Sahelanthropus 7 Ma and Ardipithecus 4 Ma walked bipedally in African woodlands. Australopithecus afarensis, Lucy, Ma showed mixed arboreal terrestrial traits. Mammals peaked in diversity, giant armadillos, toxodons in South America, hippos, giraffes in Africa. The Quaternary period, 2.6 Ma present, brought the ice ages. Pleistocene epoch, 2.6 Ma 11,700 years ago, featured cyclic glaciations driven by Milankovitch orbital variations, amplified by low Co 2, 180-280 ppm during cycles and continental positions. Ice sheets advanced, retreated 20 times, lowering sea levels 120 meters during peaks, exposing land bridges, Beringia, Doggerland. Megafauna thrived, woolly mammoths, saber-toothed cats, Smilodon, giant ground sloths, Megatherium, 6 tons, cave bears, Irish elk with 3-meter antlers. Humans evolved, Homo habilis 2, 3 Ma used tools, Homo erectus, Ma migrated out of Africa, controlled fire, Neanderthals 400,000 adapted to cold. Homo sapiens 300,000 emerged in Africa, spreading globally by developing art, agriculture 12,000. The Holocene epoch, 11,700 present, began with warming, leading to civilization. But human activity now drives the Anthropocene, unofficial, with Co 2 at 420 ppm, warming, biodiversity loss. From fiery birth to animal haven, Earth's journey, cooling, oxygen rise, life explosion, culminated in a world teeming with creatures, volcanoes tamed underground, sustaining habitability. We now arrive at the most recent chapter in Earth's epic transformation, the Quaternary period, from 2.58 million years ago to the present day, encompassing the Pleistocene ice ages and the Holocene interglacial in which human civilization arose. At this stage, the planet had long completed its journey from a molten, volcano-blanketed fireball to a stable, oxygen-rich, biologically vibrant world. The rampant surface volcanism of the Hadean and early Archean had been fully internalized for billions of years. Magma now rises only along well-defined tectonic boundaries. Subduction zones feed arc volcanoes, mid-ocean ridges quietly extrude new basaltic crust, and occasional mantle plume hotspots produce flood basalts or island chains. These processes continue to recycle carbon, regulate climate over geological timescales, and supply trace nutrients to the biosphere, but they no longer dominate the surface as they once did. The Earth of the Quaternary is recognizably modern in its broad geophysical outline. Continents in roughly their present positions, oceans circulating in familiar patterns, and an atmosphere whose composition, approximately 21% oxygen, 78% nitrogen, and trace greenhouse gases, sustains complex multicellular life across every major biome. The Quaternary is defined above all by repeated glacial-interglacial cycles, driven primarily by Milankovitch orbital variations, eccentricity, obliquity, and precession that modulate the distribution of solar insolation, especially at high northern latitudes. These astronomical forcings are amplified by powerful Earth system feedbacks, changes in ice sheet albedo, shifts in ocean circulation, notably the Atlantic meridional overturning circulation, variations in atmospheric CO2 and methane concentrations, and dust loading from expanded arid zones. During glacial maxima, CO2 levels fell to 200 ppm and methane to -350-500 ppb, largely because colder oceans absorbed more CO2 and wetlands that produce methane shrank or froze. During interglacials, including the current Holocene, CO2 rose to -280 ppm and methane to 800 ppb before the Industrial Era. The Pleistocene epoch, 2.58 ma 11,700 years ago, witnessed at least 20-25 major glacial-interglacial cycles, with the most recent ones, the last ~800,000 years, showing particularly large amplitude, ~100-120 m sea level change, for 7 degrees C global temperature swings. During peak glaciation, most recently the last glacial maximum LGM ~26 519,000 years ago, ice sheets up to 3-4 km thick covered much of northern North America Laurentide, northern Europe Fennoscandian, the British Isles, parts of Siberia, and the Patagonian Andes. Alpine glaciers descended far below modern tree lines, and sea level stood ~120-130 meters lower, exposing vast continental shelves. The Sunda Shelf connected Southeast Asia to Indonesia and Borneo. The Sahel Shelf joined Australia to New Guinea and Tasmania. Beringia formed a broad land bridge between Siberia and Alaska. These cold, dry conditions profoundly shaped ecosystems. In unglaciated regions, tundra, steppe, and cold desert dominated high and mid-latitudes. Mammoth Steppe, a cold, grassy biome rich in herbs, sedges, and forbs, supported one of the most spectacular megafauna assemblages ever known. In Eurasia and North America we find woolly mammoth, Mammuthus primigenius, up to 4 m at the shoulder, with curved ivory tusks up to 4 m long, thick subcutaneous fat, and a double coat of guard hairs and underwool. Woolly rhinoceros Coelodonta antiquitatis, a two-horned browser with heavy fur and nasal turbinates to warm inhaled air. Giant deer Megaloceros giganteus, Irish elk, whose antlers spanned up to 3.65 m and weighed 40 kg, likely used for display rather than combat. Steppe bison Bison priscus, larger than modern bison with massive humps and long horns. Cave lion Panthera larger than modern African lions, and cave hyena Crocuta spelea. Short-faced bear Arctodus simus in North America, possibly the largest terrestrial carnivore of the Pleistocene at 900 kg. Saber-toothed cats Smilodon fatalis in North America, Homotherium in Eurasia, with elongated upper canines for precise throat strikes. In South America, isolated by the rising Andes and the eventual closure of the Isthmus of Panama, 3 Ma, the Great American Biotic Interchange brought North American carnivores south and South American marsupials and xenarthrans north. Megatherium giant ground sloth up to 6 tons browsed high foliage. Glyptodonts armored relatives of armadillos weighed up to 2 tons. Toxodon, a rhinoceros-sized node ungulate, grazed steppe-like plains. Australia, isolated since the Eocene, retained its unique marsupial megafauna. Diprotodon wombat-like 2-3 tons, Procoptodon short-faced kangaroo up to 3 m tall, Megalania varanus priscus, a 7 m monitor lizard, and Thylacoleo marsupial lion with powerful bite. In Africa and southern Eurasia, megafauna included straight-tusked elephants, Paleozoic antiquus, giant hartebeest, Civathurium, giraffe-like with ossicones, and early Homo species. Hominins evolved rapidly during the Pleistocene. Early Homo erectus/ergaster, Ma already used fire and Acheulean hand axes. By 800 300,000 years ago, archaic Homo sapiens and Neanderthals H. neanderthalensis appeared with larger brains 1400–1600 cm3, complex tool industries, Mousterian, burial practices, and evidence of symbolic behavior, ochre use, ornaments. Neanderthals adapted to cold Europe and Western Asia, hunting large game with thrusting spears, using medicinal plants, and possibly creating cave art. Denisovans, known from DNA in Siberian cave sediments, interbred with both Neanderthals and early modern humans. Anatomically modern Homo sapiens emerged in Africa 200,000 years ago. By 50,000 years ago, behavioral modernity, art, music, long-distance trade, advanced projectile weapons coincided with dispersal out of Africa. Modern humans reached Australia by years ago, Europe by years ago, and the Americas by at least 15,000 years ago, possibly earlier. During this expansion, many megafauna species disappeared in a staggered pattern often called the Quaternary Extinction event. The causes of the late Pleistocene megafaunal extinctions, 4,000 years ago, remain debated, but most researchers now favor a synergistic multiple stressor model. Rapid climate change at the end of the last glacial period, 11,700 years ago, shifted biomes, fragmented habitats, and reduced steppe productivity. Human hunting pressure, especially with Clovis points in North America, 13,000 years ago, and sophisticated spear throwers elsewhere. Fire use altering landscapes, disease introduced by humans or commensals. Australia lost 55 kg plus species, 90% of its megafauna, shortly after human arrival. North America lost 35 genera, 70% of megafauna, 44 kg, at the end of the Pleistocene. South America and Eurasia suffered staggered losses. The Holocene epoch, 11,700 years ago to present, began with abrupt warming at the end of the Younger Dryas cold snap, 911,700 years ago. Temperatures rose 47 degrees C in decades in the North Atlantic region. Sea level rose rapidly, 1 m per century initially, and biomes shifted poleward. Megafauna extinctions continued in some regions, e.g. woolly mammoth on Rangel Island until years ago, but surviving large mammals, elephants, rhinos, giraffes, bison, bears, persisted in Africa and southern Asia. Humans transitioned from hunter-gatherer societies to agriculture in multiple independent centers between and years ago. Fertile crescent wheat, barley, goats, sheep. 10, 509,000 years ago, Yangtze and Yellow River valleys, rice, millet, pigs, Mesoamerica, maize, beans, squash, Andes, potatoes, llamas, New Guinea highlands, taro, bananas. This Neolithic revolution led to settled villages, pottery, domesticated animals, and eventually cities, writing, metallurgy, and complex societies. Population grew from 510 million at the start of the Holocene to 1 billion by 1800 CE. Climate during most of the Holocene was relatively stable, with minor fluctuations. The Holocene climatic optimum, 9,000 years ago, was 2 degrees C warmer than the 20th century baseline in many regions. The neoglacial cooling began years ago. The medieval warm period, 950–1250 CE, and Little Ice Age, 1300–1850 CE, were regional phenomena superimposed on a gradual cooling trend until anthropogenic greenhouse gas forcing reversed it. The last 2 centuries mark the Anthropocene, an informal but widely discussed interval in which human activity became the dominant driver of planetary change. Industrialization, fossil fuel combustion, deforestation, fertilizer use, and land use change have increased atmospheric CO2 to 420 ppm, methane to 1,900 ppb, and nitrous oxide to 335 ppb 2025 values, driving 1 to 1.5 degrees C warming since pre-industrial times. Biodiversity is declining at rates 101,000 times background extinction. Ocean acidification is lowering pH by 0.1 units. Nitrogen and phosphorus cycles are massively perturbed. Plastic pollution and synthetic chemicals are ubiquitous. Yet the same technological and scientific advances that created these pressures also allow us to understand Earth's 4.6 billion year history. From a glowing ball of molten rock with no oxygen and volcanoes everywhere, to a blue planet with breathable air, stable continents, and a biosphere rich enough to support billions of conscious beings capable of reflecting on their own origins. The volcanoes that once defined the surface have retreated to the interior, becoming the unseen engine of plate tectonics and long-term habitability. The oxygen that was absent for billions of years now sustains our every breath. The animals that took hundreds of millions of years to evolve now share the planet with a single species powerful enough to reshape it, for better or worse. This is the story so far, from fire to life, from chaos to complexity, from a barren rock to a world alive with wonder. We have now reached the very edge of the present moment in Earth's long story, the transition from deep geological time into the accelerating present and the uncertain near-future horizon. The Quaternary period continues, but the last few centuries have introduced a fundamentally new chapter, one in which a single species, Homo sapiens, has become the dominant force shaping the planet's surface conditions, atmospheric composition, biological diversity, and even the long-term trajectory of habitability itself. The volcanoes that once defined the entire surface of the young Earth have remained firmly underground for billions of years. Their activity is now confined to narrow tectonic belts, rift zones, subduction arcs, and scattered mantle hotspots. They continue to play their quiet, indispensable role, outgassing carbon dioxide and other volatiles that help regulate the carbonate-silicate cycle, supplying trace metals to the oceans, creating new islands, and occasionally reminding humanity of their power through dramatic but localized eruptions. Yet the primary driver of environmental change today is no longer volcanism, nor orbital cycles, nor even biological evolution in the classical sense. It is industrial and agricultural activity powered by the combustion of ancient fossil carbon. Let us first step back to the closing millennia of the Pleistocene and the opening of the Holocene to see how the stage was set. By approximately 12,000 years ago, the last major glacial retreat was underway. The massive Laurentide and Fennoscandian ice sheets were melting rapidly, releasing enormous volumes of freshwater into the North Atlantic and raising global sea level by roughly 120 meters over several thousand years. This meltwater pulse disrupted ocean circulation patterns, most famously contributing to the abrupt Younger Dryas cold snap, (12, 911,700 years ago, a brief return to near glacial conditions in the northern hemisphere caused by the shutdown or weakening of the Atlantic Meridional Overturning Circulation, AMOC. Once that freshwater pulse subsided, the Holocene warming resumed and stabilized. Temperatures in many regions reached or slightly exceeded mid-20th century averages during the Holocene climatic optimum, (9,000 5,000 years ago. Forests expanded poleward, the Sahara was significantly greener with lakes and rivers supporting pastoralist cultures, and coral reefs re-established themselves at higher latitudes than today. It was within this relatively stable, warm interglacial that anatomically modern humans completed their global dispersal and began the transition from mobile hunter-gatherer bands to sedentary agricultural societies. Between (12,000 and (7,000 years ago, independent centers of plant and animal domestication emerged. In the Fertile Crescent of Southwest Asia, emmer wheat, einkorn wheat, barley, lentils, chickpeas, sheep, goats, pigs, and cattle were domesticated in a mosaic of processes that unfolded over 2,000–3,000 years. In East Asia, rice, oryza sativa, cultivation began in the Yangtze Basin and millet in the Yellow River region. In Mesoamerica, maize from teosinte, beans, squash, and chili peppers were gradually transformed through selective breeding. In the Andes, potatoes, quinoa, llamas, alpacas, and guinea pigs were domesticated. In New Guinea and surrounding islands, taro, bananas, and sugar cane were cultivated early. This Neolithic demographic transition dramatically increased human population density in favorable regions, from perhaps 1.5 people per square kilometer among hunter-gatherers to 5,200 per square kilometer in early farming villages. Permanent settlements appeared: Jericho (9 600 BCE), Saddlehuruk (7 400 6400 BCE), Göbekli Tepe (9 600 8200 BCE), a monumental ritual complex built by pre-agricultural or early agricultural societies, and early Chinese villages along the Yellow and Yangtze rivers. Agriculture and sedentism triggered cascading ecological changes. Forests were cleared for fields, leading to accelerated soil erosion in many regions. Irrigation in Mesopotamia and the Indus Valley caused salinization of soils, contributing to the decline of early urban civilizations. Akkadian collapsed (4 200 years ago, Harappan declined (3 900 years ago. Domesticated animals concentrated methane emissions. Rice paddies became major sources of methane. Burning of vegetation for land preparation released CO2 and black carbon. By the early Holocene, these activities had already produced a detectable anthropogenic imprint on atmospheric greenhouse gas concentrations, often called the early Anthropocene hypothesis. CO2 levels, which would have declined toward 240–260 ppm in a purely natural interglacial, instead stabilized around 260–280 ppm. Methane rose above the expected natural interglacial value. The Bronze Age (3 300–1200 BCE) and Iron Age (1 200 BCE onward) saw the rise of complex societies, metallurgy, writing, long-distance trade, and larger-scale deforestation and land modification. Cities like Uruk, Memphis, Mohenjo-Daro, Anyang, and later Athens, Rome, Chang'an, and Teotihuacan each required hinterlands of thousands of square kilometers to supply timber, charcoal, grain, and pasture. The Roman Empire alone is estimated to have cleared 50–60 million hectares of Mediterranean forest, contributing to regional soil degradation and silting of harbors. Despite these impacts, the overall scale remained regional. Global population stayed below 300 million until 1000 CE and reached only 500-600 million by 1700 CE. Atmospheric CO2 remained 275-285 ppm and methane 800 ppb throughout most of the pre-industrial Holocene. The decisive acceleration began in the mid-18th century with the Industrial Revolution, initially in Britain and then spreading to Western Europe, North America, and later East Asia. Coal, followed by oil and natural gas, replaced wood and charcoal as the primary energy source. Steam engines, mechanized textile production, railroads, steamships, and later internal combustion engines and electricity transformed economies and societies. The consequences for Earth's surface and atmosphere were profound. Fossil fuel combustion released hundreds of billions of tons of carbon that had been sequestered over hundreds of millions of years, raising atmospheric CO2 from 280 ppm in 1750 to 420 ppm today. Land use change, deforestation for agriculture, pasture, timber, and urban expansion has reduced global forest cover by roughly 30–40% since the pre-agricultural Holocene maximum. Nitrogen and phosphorus cycles have been massively perturbed through the Haber-Bosch process, synthetic ammonia, and phosphate mining, leading to widespread eutrophication of lakes, rivers, estuaries, and coastal zones. Synthetic chemicals, pesticides, plastics, fluorinated compounds, flame retardants have become globally distributed, even in remote polar ice and deep ocean sediments. Species extinction rates are estimated to be 101,000 times higher than the pre-human background rate, with many biologists arguing we are in the early stages of the sixth mass extinction. The warming produced by these changes, currently 1 to 1.5 degrees C above the 1850–1900 baseline, is already measurably altering almost every component of the Earth system. Glaciers and ice sheets are losing mass at accelerating rates. Greenland and Antarctica combined contribute to 81 mm/ or to sea level rise. Ocean heat content has increased dramatically, with 90% of excess heat from greenhouse gas forcing absorbed by the ocean. Coral reefs are experiencing mass bleaching events at frequencies never recorded in the Holocene. Permafrost thaw is releasing stored methane and CO2, creating a positive feedback. Extreme weather events, heat waves, heavy precipitation, intense tropical cyclones are becoming more frequent and severe in many regions. Phenological shifts, earlier springs, later autumns, and poleward range shifts of species are widespread. Looking forward, the trajectory of Earth's habitability now depends heavily on human choices made over the next few decades. Multiple lines of evidence, paleoclimate records, current observations, and Earth system models suggest that, if emissions peak soon and decline rapidly toward net zero by mid-century, warming can plausibly be limited to 2 degrees C, preserving many coral reefs, reducing the probability of crossing major tipping elements, Amazon dieback, West Antarctic ice sheet collapse, Greenland ice sheet disintegration, permafrost carbon release, and keeping sea level rise this century below 0. 51 m if emissions continue on a high pathway, roughly current policy trajectories. Warming of 3–4 degrees C or more by 2100 becomes likely. With multi-meter sea level rise over centuries, widespread ecosystem transformation, severe risks to food production in the tropics and subtropics, and greatly elevated probabilities of crossing irreversible tipping points. Even in the most optimistic stabilization scenarios, many changes already underway: loss of low-latitude glaciers, coral reef degradation, poleward migration of climate zones are effectively irreversible on human timescales. Yet the Earth system retains enormous resilience. The long-term carbon cycle, weathering of silicate rocks, will eventually remove excess CO2 over tens to hundreds of thousands of years. Oxygen levels are buffered by the vast reservoir in the atmosphere and oceans. Plate tectonics and mantle convection will continue operating for billions of years, maintaining the geophysical conditions necessary for a habitable surface. In the very long view, millions to billions of years, the sun's gradual brightening will eventually render Earth uninhabitable regardless of human actions, but that lies far beyond the scope of the Anthropocene or even the Quaternary. For the foreseeable geological future, the planet's capacity to support complex animal life, including our own species, remains intact, provided we manage the extraordinary power we now wield over the atmosphere, biosphere, and land surface. Thus concludes the narration of Earth's transformation, from a seething, oxygen-free ball of molten rock and lava seas, to a world where volcanoes have retreated to the interior. Oxygen became abundant through photosynthetic life, continents stabilized, oceans teemed with animals, forests rose, ice ages came and went, and finally a single intelligent species emerged capable of both destroying and consciously preserving the conditions that made all of this possible. The story is not over. It is being written every day by billions of human decisions, large and small. The fiery birth has become a living, breathing present, and, if we choose wisely, a sustainable future. As we reach the culmination of this grand narrative, let us reflect on the extraordinary odyssey of our planet, from its violent, incandescent beginnings as a swirling mass of molten rock and endless lava flows, where volcanoes dominated every inch of the surface and oxygen was nowhere to be found, to the vibrant, life-sustaining world we inhabit today. Over the course of these 15 parts, we've traced the slow retreat of those primordial volcanic forces into the Earth's interior, the mantle's convective churn confining eruptions to plate boundaries and hot spots, allowing a stable crust to form. We've witnessed the emergence of oceans from condensed volcanic vapors and cometary deliveries, the oxygenation of the atmosphere through ancient microbial toil, and the step-by-step assembly of conditions that made the planet habitable first for simple life, then for complex ecosystems, and finally for the diverse array of animals that roam its lands, seas, and skies. In this final part, we'll synthesize the key milestones, explore the implications for our current era of human dominance, and gaze ahead to what the future might hold for Earth's habitability. We'll delve deeper into the mechanisms that drove these changes, drawing on geological, biological, and climatic insights to provide a comprehensive capstone to our story. Remember, this is not just a tale of rocks and gases. It's the biography of a world that birthed us all, a reminder of the fragility and resilience intertwined in every layer of its history. Let's begin by recapping the Hadean and Archean foundations with greater detail, as these eras set the stage for everything that followed. Some 4.6 billion years ago, the solar nebula's dust and gas coalesced into planetesimals that collided to form proto-Earth. The heat from these impacts, combined with radioactive decay and gravitational differentiation, melted the entire planet into a magma ocean hundreds of kilometers deep. Volcanoes weren't isolated features. The surface was a continuous volcanic expanse, with silicate lavas flowing like rivers of fire, gas bubbles exploding into proto-atmospheres of steam, carbon dioxide, and sulfur compounds. No oxygen existed in free form. It was bound in oxides like silica or iron oxides. The moon-forming impact with Theia-4, 5 Ga ejected debris that cooled into our satellite, stabilizing Earth's tilt and tides, but it also remelted much of the surface, prolonging the fiery phase. As heat radiated into space, the magma ocean crystallized from the bottom up, forming a basaltic crust floating on a partially molten mantle. Early plate tectonics, primitive subduction and spreading began recycling this crust, pulling volcanic activity inward. Zircons from Jack Hills, Australia, 4 Ga, preserve evidence of liquid water by 4 3 Ga, as isotopic ratios indicate interaction with granitic rocks formed in the presence of water. Comets and carbonaceous asteroids delivered volatiles, but volcanic outgassing contributed most of the early atmosphere and hydrosphere. The atmosphere remained reducing with methane and ammonia until UV photolysis and escape stripped light gases, leaving CO2 and N2 dominance. The volcanoes entering the center metaphor captures this transition, from surface-wide effusions to focused vents as the lithosphere thickened to 100 km by the end of the Archean. Ga. Mantle plumes like those today under Hawaii or Yellowstone were more vigorous then due to higher internal heat, till the 200–300 degrees C hotter mantle, producing large igneous provinces that covered continents in basalt layers kilometers thick. These events, such as the Ga-Matashuan Dike swarm, released gases that influenced climate but were no longer global catastrophes. Life's emergence around. 3.5 Ga in hydrothermal vents, black smokers where volcanic heat met seawater, marked the shift toward habitability. Chemosynthetic archaea and bacteria harnessed energy from mineral gradients, evolving into cyanobacteria that performed oxygenic photosynthesis by ~3. 2.7 Ga the Great Oxidation Event ~2, for 2.2 Ga oxidized dissolved iron, forming banded iron formations, e.g. Hammersley Range ~2, 5 Ga, and began accumulating free O2, but levels stayed low ~0, 1% Pal, until the Neo-Proterozoic ~0, 80.6 Ga, when another oxygenation pulse reached 20% Pal, enabling eukaryotic complexity in the Ediacaran biota. The Phanerozoic Eon ~541 Ma present saw animal life's explosion. The Cambrian radiation introduced bilaterian body plans, biomineralization and predation, fueled by rising oxygen and nutrient fluxes from weathering. Ordovician diversification built reefs. Silurian Devonian saw vascular plants colonize land, roots deepening soils, and tetrapods emerge. 375 Ma Tiktaalik. Carboniferous coal forests spiked oxygen to 35% Pal, enabling giant arthropods like Arthropleura. Permian synapsids dominated before the end Permian extinction. 252 Ma, triggered by Siberian traps volcanism releasing GTCO2, warming 810 degrees C and causing ocean anoxia. Mesozoic recovery birthed dinosaurs 232 Ma, pterosaurs, marine reptiles, and eventually birds 150 Ma, Archaeopteryx. Cretaceous angiosperm rise revolutionized food webs. Tyrannosaurs and hadrosaurs peaked before the Chicxulub impact. 66 Ma, Km bolide and Deccan traps, Km3 lava extinguished non-avian dinosaurs. Cenozoic mammals radiated, Eocene giants like Indricotherium, Miocene grasslands favored grazers, Pliocene hominids like Australopithecus 4 Ma walked upright. Quaternary ice ages, Ma present sculpted landscapes with megafauna thriving until human-driven extinctions, 50,000 10,000 years ago. In the Holocene, 11, 7 Ka present, agriculture and industry amplified human impact. Today, with 8 billion people, we're altering the planet at geological scales. CO2 at 420 ppm drives degrees C warming. Biodiversity loss rivals mass extinctions. Plastic microplastics permeate ecosystems. Looking ahead, if emissions stabilize, Earth remains habitable for millennia. But high emission paths risk tipping points. AMOC collapse, Amazon dieback, permafrost thaw adding 100–200 GT carbon. Over millions of years, plate tectonics will rearrange continents, perhaps forming a new supercontinent, 250 Ma, Pangea Ultima, altering climate. The sun's luminosity increase, 1% per 110 Ma, will eventually boil oceans, 1 Ga, but until then, life's adaptability, honed over 4 Ga, ensures persistence. This documentary has spanned eons, from lava worlds to animal kingdoms. The Earth's story is one of transformation, resilience, and interconnection. And now, as we wrap up this journey, if you've enjoyed exploring the epic history of our planet, be sure to subscribe for more captivating documentaries like this one. Drop a comment below sharing your thoughts, what surprised you most about Earth's evolution. and let us know where you're watching from, whether it's a bustling city or a quiet corner of the world. Your engagement keeps these stories alive.